could there be, beyond the three familiar dimensions of space and the single arrow of time? As many as 11 additional dimensions of space? And if there are, what might be hiding inside them? This question hangs in the air like an impossible window opening onto a room the size of a universe. It is a question that strains the imagination and tugs at a deep, almost primordial unease, the sense that what is missing from human history may not be missing at all, but merely invisible to the senses and instruments that evolved to navigate a three-dimensional world. It presses upon the mind with the same quiet urgency as a fossil fragment found in a rock face, small, enigmatic, and capable of rewriting entire narratives. The first reaction is usually wonder, the uncomplicated electrical thrill of possibility. Many feel it as a pinch in the chest, a sudden dilation of perspective, the comfortable box of everyday reality expanding into a place where entire structures, entire epochs of action, could be coiled away like threads beneath a carpet. Beneath that comes a colder sensation, dread of the unknown, the fear that human knowledge is so narrowly tuned that whole branches of reality pass unnoticed. Together these emotions form a human duet, curiosity pushing forward, caution pulling back. They shape the way questions are asked, the experiments conceived, the stories told to explain why the world appears the way it does. To approach the idea of hidden dimensions, a mind must learn to be both patient and impatient. Patient with the mathematics that suggest their existence, impatient with the intuition that refuses them. The mathematics of modern theoretical physics permits and sometimes requires additional spatial dimensions. In the language of those equations, extra dimensions can be compactified, curled up at scales so small they defy direct observation, or structured into shapes so complex they act like folded origami beyond human comprehension. These are not merely fanciful add-ons, they are the scaffolding upon which certain unified models of reality rest. But equations are not evidence, they are proposals, maps that may or may not correspond to the terrain. A convenient and vivid way to imagine an extra dimension is through an analogy. Consider a tightrope. To a flea living on that rope, the world is one-dimensional. It can go forward and backward. From a human perspective, the rope itself occupies a line through space. But humans can step off it in a second dimension and see the rope from above. Now imagine curious phenomena that the flea could never describe, patterns in the rope's weave visible only from above, or a shadow of a bird passing that the flea perceives as a terrifying, inexplicable wind. The flea's ignorance is not stupidity, it is a limitation of its embedded perspective. Likewise, a civilization or a geological record confined to three spatial dimensions might be blind to structures that extend into a fourth or fifth spatial dimension. That blindness would not erase those structures, it would render them manifest in ways that seem anomalous, shadows, distortions, unexpected alignments. Earth itself is a masterclass in erasure. Deep time is a sieve with a relentless appetite. Mountains rise like living things, only to be ground down by weather and time. Ocean basins open and close as continents drift on slow and different currents of rock. Glaciers polish valleys and then melt, leaving their fingerprints in faint striations. The overwhelming majority of the planet's surface and its artifacts have been recycled, metamorphosed, or swallowed into the deep. Rocks that once recorded the detailed story of an ancient city might be melted and recrystallized by tectonic processes. Delicate organic materials crumble into chemical whispers, entire sedimentary archives are subducted and remade. The geological memory of the world is partial, biased, and prone to erasure. This is why the fossil record is fragmentary, why vast stretches of Earth's epochs remain sparsely documented. If human civilization, or any civilization, had risen and fallen many hundreds of thousands or millions of years ago, the odds are overwhelmingly that its most tangible traces would be gone. Stone becomes dust, metal oxidizes into compounds indistinguishable from naturally occurring minerals. Organic matter returns to the great chemical soup. The problem becomes more acute when the time scales involved approach those of plate tectonics. What was once surface becomes mantle, and with it, the visible history of beings who left marks on the crust. The archive of Earth is biased toward the robust, the long-lived, and the miraculous mineralized bones, certain types of stonework, and rare, isotopic anomalies. This natural tendency to erase is one reason the question of hidden dimensions acquires emotional force. It offers an alternative form of preservation, an escape hatch from the sieve. What are some aspects of past existence that not depend primarily on matter that could be ground away, but on geometry, on relationships, on the arrangement of space itself? What if information could be stored not in physical artifacts, but in the curvature, topology, or folded structure of dimensions beyond ordinary perception? In such a case, an advanced civilization, or a natural process that imprinted significant events, might leave signatures that evade conventional archaeology and paleontology, but might reveal themselves as subtle deviations in gravitational fields, inexplicable distributions of energy, or anomalies in the crystalline lattice of deep minerals. The mind reaches for analogies again. Consider a library whose books are not printed on pages, but encoded into the weave of a carpet. From the surface, the carpet is a pattern, perhaps ornate, perhaps seemingly random. Only the appropriate key, a method for unfurling the weave into a readable format, would yield the embedded stories. From a three-dimensional perspective, an intelligent design that lives across extra dimensions would be like that library, a storehouse of patterns that only a higher dimensional perspective could read. To a three-dimensional observer, the library manifests as a set of oddities, regions of carpet that resist wear, threads that align into non-random motifs, and occasional glimpses of characters when the light hits at a proper angle. It invites a different kind of investigation. Another avenue lies in the idea of projection. Three-dimensional objects cast two-dimensional shadows. Similarly, structures with four or more spatial dimensions would cast three-dimensional shadows into our perceivable world. These shadows might be grotesquely deformed analogues of the original, changing in inexplicable ways as they intersect with our space. An advanced civilization manipulating higher dimensional geometry could produce effects that look miraculous, dangerous, or simply incomprehensible. Imagine a colossal, higher-dimensional edifice intersecting Earth's 3D space. What would appear would be a sight of odd gravity gradients, sudden shifts in volume, perhaps brief appearances and disappearances of matter. Yet once the intersection passes, the evidence might be gone except for subtle residual effects, a rearranged mineral grain, a local magnetic anomaly, an isotope ratio slightly off the expected norm. In terms of detectability, this scenario is maddeningly subtle. Physics offers breadcrumbs where to look. Extra-dimensional models predict a variety of phenomena, altered behaviors of gravity at very small scales, unusual particle resonances, or topological defects that survive as relics. These predictions are precise enough to guide experiments, yet they remain notoriously difficult to probe. Gravity is the weakest of the fundamental forces at the scales of everyday life. It is also the one most likely to be affected by additional dimensions. Tiny deviations from Newtonian expectations in laboratory experiments, or unexpected modes in gravitational wave data, could be suggestive. So, too, could subtle anomalies in the distribution of matter in the cosmos, strange thermal signatures in the deep subsurface of Earth, or patterns in the magnetization of ancient rocks that do not fit geomagnetic models. Each anomaly is not proof so much as an invitation. Investigate, measure, refine, and imagine. There is also the question of intent. If extra dimensions can serve as repositories, were they used intentionally? The human tendency to leave messages for the future takes many forms. In the absence of preserved monuments, perhaps a species would choose to encode its history in a way that evades the geological grinder, set up a pattern in crystal lattices, seed certain isotopic ratios in long-lived reservoirs, or manipulate space-time geometry to produce a specific signature detectable by those with the right theoretical apparatus. This is a speculative hypothesis, but it is also a statement about what intelligence values: memory, continuity, and the hope to be known. The choice to hide in higher dimensional spaces might be an ultimate act of humility or an act of preservation against the entropy of matter. There is a distinct melancholy to these hypotheses. If entire civilizations were folded away into dimensions humans cannot see, then the fragments that remain, if any, may be stubbornly ambiguous. A peculiar mineral grain might be dismissed as a quirk of formation. A localized isotopic spike could be relegated to volcanic outgassing. A gravitational deviation might be explained by instrument error. The silence of the geological record is not evidence of absence so much as evidence of limitations of method, of perspective, of the species itself. The possibility of hidden dimensions reframes that silence. Silence can be thick and meaningful, a white noise of things kept out of view. Yet, to move from romantic speculation to a discipline of inquiry requires a tempering of wonder with rigor. The scientific method thrives on testable predictions. Theories involving extra dimensions make such predictions, albeit challenging ones. Experiments push at the edges, particle colliders searching for energy loss into extra-dimensional modes, precise torsion balance. Experiments searching for deviations in gravity at sub-millimeter scales, analyses of gravitational wave signatures that could carry imprints of higher dimensional dynamics. At the same time, geoscientists refine their readings of Earth's deep record, casting a wider net for anomalies, reinterpreting oddities not as noise but as potential clues, and collaborating with theorists to identify what a higher dimensional imprint might look like in a rock rather than on an equation. Beyond formal experiment, there is the slow, patient work of narrative archaeology, re-examining myths, oral traditions, and symbolic systems for consistent references to anomalies in the sky, ground, or time. Such patterns have historically guided investigations. They can point to places where the geological record should be scrutinized more carefully. Caution is essential here. Myth is malleable and often metaphorical. Still, it can store patterns of observation across generations, sometimes echoing real events in coded form. If extra-dimensional events intersected with the human-scale world in dramatic ways, they might leave traces in collective memory stories of sudden transformations, objects appearing and vanishing, and lands rearranged overnight. These echoes would not be evidence in themselves, but they would be a kind of cultural residue demanding scientific attention. The emotional undercurrent persists throughout, awe at the scale of possibility and humility before the limits of perception. There is also a quiet hope. The idea that something might be hidden does not negate the possibility of discovery, it simply shifts the terms. Discovery becomes an act of translation, finding the key that allows humans to read a different kind of archive. The thrill of such a translation is both scientific and profoundly human. It is the same impulse that led early astronomers to map the heavens, paleontologists to assemble bones into creatures, and linguists to decode dead scripts. To decipher a higher dimensional record would require an expansion of tools, of imagination, and of patience. It would require bridging disciplines that rarely speak to one another, high-energy physics with deep-time geology, topology with oral history. At the scale of a single human life, the question can feel unbearably remote. But, viewed through deep time, each generation becomes both a fleeting observer and a potential translator. The world has always been stranger than the immediate senses allow, and yet the human species has built instruments and narratives that extend perception. The possibility of 11 more dimensions is a reminder that extension is ongoing. What is hidden today may be accessible tomorrow through computation, instrumentation, and a willingness to look where earlier generations did not think to look. The idea is also morally provocative. If histories can be sequestered in ways that elude discovery, then so can narratives of harm. Ignorance or triumph, the ethics of concealment and preservation assume new weight. Who decides what is to be archived beyond time's grinding hand? Who has access to the keys? These are questions as old as memory itself, but transposed into a cosmic register. They demand humility. Progress that expands perception should be pursued with a sense of responsibility, for the act of uncovering carries consequences for how humanity understands itself and its place in a possibly vaster tapestry. In the immediate term, the question is a clarion call for interdisciplinary curiosity. It asks geologists to listen to subtle anomalies. It asks physicists to translate mathematical elegance into observational strategies. It asks philosophers to consider what it means for a history to be hidden. It asks the public to hold both wonder and skepticism. Above all, it asks to be taken seriously, not as a fantastical dodge from the hard work of science, but as a legitimate axis for inquiry grounded in real theoretical possibilities and real empirical challenges. There is a final, quieter truth in the proposition. Whether or not 11 extra dimensions exist, the act of asking the question reshapes the way humans attend to their world. It enlarges the canvas of curiosity and deepens the humility with which the species approaches its own short tenure on a geological stage. It reframes the silence of the deep past, not as a defeat, but as a puzzle that invites generations to refine their tools, polish their instruments, and sharpen their imaginations. The question, could there be 11 additional spatial dimensions, and what hides within them, is less a matter-of-fact query than a doorway. On the other side waits a sequence of investigations, mathematical deep dives into topology and compactification, careful scrutiny of the geological strata for anomalous signatures, searches for physical deviations that refuse simple explanation, and the patient work of reconstructing possible strategies for preservation beyond 3 dimensions. Each of these pathways is itself an adventure in thinking, a slow excavation of possibility. For now, the question remains the beginning, a faint, persistent knock on the door of the known. The next part to the inquiry will open that door further, examining the tools, the clues, and the consequences, and will test whether the hidden rooms, if they exist, can ever be illuminated by a species that has only just begun to learn how to listen. What if the most radical shift in humanity's understanding of reality did not come from discovering a new thing at all, but from changing what questions were permitted to be spoken aloud? What if the story of how people came to think about space and time is, in essence, the story of how minds learn to see the world not as a static theater in which events occur, but as a malleable fabric whose very shape can carry meaning? The intellectual lineage that runs from Democritus to Einstein is not merely a catalogue of names and equations. It is a slow, cumulative reimagining of what counts as the substance of the universe. Each turn, philosophical, mathematical, experimental, was an emotional and conceptual wrench that prized the comfortable image of reality into something stranger. To follow that lineage is to trace how the idea of building blocks gave way to fields, and fields in turn yielded to geometry. It is a path that moves from the discrete to the continuous, from objects to relations, and finally to the very shape of space-time itself as an active participant in the cosmic drama. Democritus's atomism arrived like a cool, skeptical breeze across the sunlit plazas of ancient Greece. The notion was astonishingly simple and audacious. The visible world, in all its multiplicity, could be explained by a plurality of indivisible units, atoms moving through empty space. It was a radical demotion of the visible into the invisible and the immeasurable into the countable. The emotional texture of that idea flickers between liberation and loneliness. To assert that things are nothing more than agglomerations of tiny, enduring bits was to propose a universe without teleology, without an intrinsic narrative shaped by gods or forms. For minds inclined to seek purpose, there was a sting in that reduction. For others, there was exhilaration, a new economy of explanation, a promise that complex phenomena might yield to patient enumeration and combinatorial reasoning. Yet atomism also contained an implicit humility. If the world could be decomposed into minute particles and the void between them, then the senses were revealed as partial instruments, good for living, poor for knowing. The emotional effect on later thinkers was a lingering, productive tension. Curiosity sharpened by a suspicion that reality extended beyond immediate perception. That suspicion seeded centuries of thought, debates about continuity versus discreteness, about whether nature's essence could be captured by indivisible chunks or by smooth, unbroken flows. Between Democritus and modern physics, centuries of philosophical elaboration wove other threads into the tapestry. Plato and Aristotle argued for forms and substances. Scholastic thinkers sutured these perspectives into theological cosmologies. Medieval scholars translated and conserved ancient texts while adding their own rigorous inquiries. The pulse of curiosity did not die, it mutated. Where atomism introduced discreteness, later developments emphasized continuity, the idea that space and time might form a kind of arena, continuous and shared, within which motion and cause are expressed. This was the terrain on which the modern scientific revolution would stride. It brought a new kind of emotional tenor, a heady confidence in the power of measurement and calculus, and an equally potent anxiety about the limits of that same power. Figures like Newton and his contemporaries offered a model of the cosmos that felt at once crystalline and consoling. Space and time, in Newton's framework, were absolute, an immutable stage and a metronome that ticked uniformly everywhere. The mathematical beauty of Newton's laws, their astounding predictive power, produced a collective exhilaration. The world made sense in predictable ways. Celestial motions were clockwork, terrestrial motion calculable. But even as that confidence mounted, fissures began to appear. The notion of action at a distance, gravity reaching across empty space, felt uncomfortable to many. How could one mass tug on another across nothingness? The success of Newtonian mechanics did not dissolve the deeper ontological worries. It shifted them. If the world were a grand machine, what sustained its gears? The emotional story here is paradoxical. Triumph accompanied by a restless unease, certainty shattered by foundational questions that would not go away. The 19th century introduced a different kind of astonishment. Maxwell's equations, unifying electricity and magnetism, revealed that fields, extended, pervasive entities were essential to understanding reality. Electromagnetism suggested that space was not merely a passive stage, but could be threaded with dynamic structures that propagated and interacted. The field concept carried with it a new emotional cadence, wonder at unity, seemingly separate phenomena collapsing into a single framework. and an increasing conviction that unseen structures, mathematical, continuous, and omnipresent, played a decisive role in physical events. At the same time, the metaphor of an ether, a subtle medium filling space to carry electromagnetic waves, offered a tempting comfort. If waves need a medium, then perhaps Newton's empty stage could be repopulated by a gentle, invisible substance. But experimental probes, notably the Michelson-Morley experiment, failed to find the ether where it should have been. The null result was profoundly unsettling. It broke the neat picture of space as a backdrop filled with a carrying medium, and it left a conceptual vacuum. How could waves propagate without a medium? The emotional response among scientists was a mixture of frustration and exhilaration. The ground was shifting beneath the edifice of accepted ideas, but fertile ground often yields the richest surprises. Into that unsettled space stepped a new kind of thought experiment, a different posture toward intuition and mathematics. Einstein's work did not emerge from a sudden epiphany detached from history. It was built on the accumulated disquiet. The failure to detect an ether, the symmetry in Maxwell's equations, the unresolved tension in dynamics. Einstein asked simple, stubborn questions. What if the laws of physics are the same for all observers in uniform motion? What if the speed of light is a constant in all inertial frames? These constraints had radical consequences. Space and time could no longer be treated as separate absolutes. Simultaneity became relative. Clocks and rulers yielded to the demands of transformation. The emotional contour of this discovery ranged from disorientation to a liberating clarity. The revelation that measurements of space and time depend on the observer dismantled old certainties and replaced them with a relational vision. Events acquire their meaning through their interrelations. Mathematics became the lingua franca of this new conception. With the recognition that the structure of space and time could change depending on reference frames, the community of thinkers needed a geometric language capable of expressing such fluidity. Bernhard Riemann's 19th century forays into the nature of geometry, considering manifolds of arbitrary dimension and curvature, provided precisely the conceptual tools. The emotional aspect here is subtle, the joy of mathematical generalization, coupled with a small vertigo at its abstraction. To move from the Euclidean intuitions that anchor everyday life to a geometry that could be curved and higher dimensional required a new willingness to be guided by formal structure rather than immediate sense. Hermann Minkowski, interpreting Einstein's special relativity, declared in an almost prophetic voice that henceforth space and time were to be considered together as a four-dimensional space-time. This union of temporal and spatial dimensions was more than a neat relabeling. It recast kinematics, dynamics, and causality in geometric terms. The heart of gravity's mystery remained. Why did bodies follow the paths they did? Einstein's subsequent step, developing general relativity, was the decisive conceptual leap. Gravity, according to this framework, was not a force acting at a distance, but a manifestation of curvature. Masses tell space-time how to curve, and curved space-time tells masses how to move. There is an emotional gravity to this idea, an aesthetic and ethical tug. To describe the universe as geometry is to ascribe to it an elegance that is at once humbling. The picture is beautiful, motion is geodesic, orbits as consequences of curvature, light deflected by the geometry through which it moves. But beauty here is not mere prettiness. It is an invitation to re-evaluate the scale of human cognition. A single set of equations can encapsulate phenomena from planetary orbits to the precession of Mercury's perihelion, and later to the bending of starlight observed during solar eclipses. The emotions these successes elicit include wonder, humility, and an expanding sense of what counts as evidence. A mathematical structure predicted an effect that telescopes later confirmed. That alignment between abstract reasoning and empirical verification is one of science's most thrilling harmonies. Yet the geometric turn did more than offer new predictive power. It subtly shifted what kinds of entities could be thought of as carriers of information. If curvature is physical, if topology and geometry influence motion and energy, then space itself can be considered a repository of relations. This is the critical conceptual bridge toward the idea that patterns need not be stored only in matter. Geometry can hold history. Topological defects, curvature distributions, and other geometrical imprints could, in principle, survive physical processes that would otherwise erase conventional artifacts. The emotional implication of that bridge is complex. On one hand, it introduces a consoling possibility that traces of events might be preserved in the structure of space-time, more resilient than the brittle histories written in organic matter. On the other hand, it deepens the mystery. Geometry is not directly accessible to intuition, and its signals can be subtle. The prospect that a past civilization or a cataclysm might have left a signature in curvature, or that a rare isotopic arrangement is the ghost of some grander geometric rearrangement, calls for both technical patience and a poetic stretch of imagination. Scientists must learn to read with microscopes and mathematics, to translate curvature into narrative, interpret the silent language of geometry. This lineage from Democritus's atoms to Einstein's curved space-time also reveals a transformation in how human beings emotionally and intellectually relate to the unknown. Where the atomists rendered nature decomposable into enduring units, the modern geometric vision emphasizes relations and form. Where early thinkers sought to account for phenomena by identifying constituent bits, later thinkers learned to see patterns as emergent properties of a deeper structure. That shift carries with it a quiet moral. Meaning can be embedded not only in objects but in the relations among them. And sometimes the most persistent records are those written into the fabric that connects. There is, moreover, an ethical cadence to the story. As the community learned to trust mathematical abstraction and to interpret its empirical echoes, the responsibility of inquiry grew. If geometry can contain history, and the way humanity manipulates space and time through energy, technology, and knowledge might imprint future strata. This thought reframes scientific progress as an act that shapes possible archives. The emotional tone here is a mixture of awe and caution, delight in the capacity to know, tempered by an awareness that the ability to alter the medium of record carries consequences. Finally, the arc from ancient atomism to general relativity sets the stage for the speculative question that has been murmuring. Since the first pages of this story, could there be aspects of history or intelligence preserved in structures beyond ordinary perception, perhaps in additional dimensions or in topologies hidden from the senses? The conceptual work of the 19th and 20th centuries makes that question less absurd. When matter and energy are not the only currencies of influence, when geometry itself can act as a medium, then the horizon of possibility widens. The mental discipline cultivated through centuries, patient measurement, rigorous mathematics, cautious interpretation becomes the toolkit for exploring that horizon. To close this chapter of intellectual history is to acknowledge both the audacity and the restraint of the scientific enterprise. From Democritus's atom, a single bold conjecture about the discreteness of matter, to Einstein's revelation that gravity is geometry, the path was marked by fits and starts, missteps and clarifications, moments of elation and long stretches of doubt. The emotional texture throughout has been varied. Wonder at unifying ideas, discomfort with counterintuitive results, the serene joy of mathematical generality, and the modesty that comes from realizing how much remains obscured. Yet these emotions are not mere ornaments. They shape the very questions asked. The humility woven through the centuries encourages a kind of patient curiosity and openness to the possibility that the archives of the past are not exhausted by the visible and the material. The courage born of intellectual triumphs permits the imagination to entertain bold hypotheses about where information might hide. Together, they forge a stance essential for the inquiry that follows, rigorous, speculative, and attuned to the whisper of anomalies. If the history of thought is a map of possibility, the path from Democritus to Einstein is the contour that allows modern minds to consider not just what exists, but how it might preserve itself beyond the erasing teeth of time. What if the simplest arithmetic of space, the count of directions in which one can move, were quietly wrong? What if the universe, in its tacit economy, hid an extra corridor that ordinary sight never walks down? This is the idea that, in the 1920s, arrived like a whisper beneath the thunder of two great revolutions, general relativity's reimagining of gravity and quantum mechanics' reshaping of matter. It was an idea both spare and extravagant, that by adding a single extra spatial dimension, the disparate forces of gravity and electromagnetism might be revealed as facets of the same geometric whole. The proposal bore the name of a mathematician and a physicist, Theodore Kaluza, and later Oscar Klein. Yet the emotional resonance of the idea belongs to something larger than a pair of biographies. It is the feeling that a small mathematical twist can open a door in the conceptual house of the world, a door whose key is not a tool, but a perspective. The world of 1920s theoretical physics was already accustomed to surprises. Space itself had been demoted from arena to actor by Einstein, and electromagnetic waves had been reframed as fields rather than mysterious telepathy through a medium. Into that charged atmosphere stepped an audacious unifier. Kaluza's thought was at once ingeniously simple and profound. Recall that Einstein had shown gravity as curvature, the metric of spacetime. The mathematical object that records distances and angles encodes gravitational effects. Kaluza asked a natural question with an unnatural willingness to be bold. What if the metric that governs distances were not four-dimensional, but five-dimensional? What if, in the extra components of that higher dimensional metric, the mathematical structure of electromagnetism could be read like a cipher? When one writes the metric in 5 dimensions and examines its components carefully, a remarkable correspondence emerges. The blocks of the 5-dimensional metric, when viewed from the 4-dimensional vantage of ordinary space-time, contain not only the familiar gravitational terms, but also quantities that behave mathematically like the electromagnetic vector potential. The equations that fall out, if one imposes a suitable constraint, resemble Einstein's equations coupled to Maxwell's equations for electromagnetism. In a single stroke, two distinct forces showed up as parts of the same geometric tapestry. Momentum in this narrative is not merely conceptual, it carries a visceral charge. There is the exhilaration of unification, the sense that separate phenomena might be different faces of a deeper symmetry, and the chill of audacity, because the idea's very neatness invited suspicion. To propose a hidden dimension is to confront an epistemic humility, the suggestion that the instruments and intuitions of the day might be blind by design. How could this be tested? How could it be reconciled with the stubborn fact that no fifth direction had ever announced itself to motion or measurement? Kaluza himself adopted a pragmatic constraint to bridge part of this gap. He assumed a cylinder condition, that nothing depended on the extra coordinate. Aha! The fifth dimension would exist in the equations but would be invisible in the sense of dynamical dependence. It was a mathematical maneuver, an elegant sleight of hand that made the derivation tidy. But the cylinder condition begged a deeper question. If the extra dimension is real yet undetectable in direct experience, how is its invisibility explained physically? Oscar Klein supplied an answer that was new and eerily modern. Drawing inspiration from quantum ideas that were concurrently altering physics, Klein suggested that the fifth dimension might be compact curled into a circle so tiny that motion around it would be imperceptible at macroscopic scales. This compactification transformed invisibility from an ad hoc assumption into a geometric hypothesis. The extra dimension is there, but it is finite and looped, its circumference so small that ordinary particles cannot resolve it. Klein realized that quantum mechanics introduces discrete momentum states around a compact circle, motion around the extra. Dimension would appear in four-dimensional terms as a spectrum of massive modes, and intriguingly, the quantum of momentum around the circle could be associated with electric charge. What had been a bookkeeping trick acquired physical texture. The Kaluza-Klein idea therefore married geometry and quantum thought. It proposed not merely that two forces could be unified by adding a dimension, but that the microscopic structure of that dimension could encode discrete properties. Charge, in the simplest, reading through wave mechanical quantization. The mathematical neatness was intoxicating. Gauge symmetry, the mathematical description of electromagnetism, emerges naturally from five-dimensional coordinate transformations. Charge conservation is mirrored in momentum conservation around the compact dimension. To the mathematical mind, this was a fusion of symmetry and economy that read like poetry, yet the emotional arc of aesthetic pleasure ran alongside a deep frustration. The compact dimension by design could be made arbitrarily small, and the associated Kaluza-Klein excitations, particles that correspond to motion in the extra dimension, would be correspondingly massive. If the radius is near the Planck scale, as would later be argued, these excitations would be far beyond experimental reach. The theory was elegant but exasperatingly silent about observables in the accessible realm of laboratories. It became an idea, admired but marginalized, beautiful on paper, tentative in practice. That fate is telling. It reveals a persistent tension at the heart of theoretical physics, the seduction of mathematical symmetry versus the discipline of measurement. Kaluza's and Klein's work planted a seed that sprouted mostly in the thought world of theorists. For decades, the concept remained a curiosum, an intriguing footnote to the larger dramas of quantum field theory and particle physics. And yet the very notion that extra geometry can masquerade as familiar forces was momentous. It shifted the imagination of what kinds of repositories reality could hold. Geometry was no longer a passive arena, but a possible medium for properties and conservation laws, even for discrete bookkeeping like charge. Seen through the lens of deep-time speculation, Kaluza-Klein acquires a particular poignancy. If information can be encoded not in durable matter, but in the shape and topology of space itself, If a civilization or process could, in principle, imprint a signature into the compact structure of additional dimensions, then the possibilities for preservation transcend the grinding appetite of geology. Geometry can be robust in ways matter is not. Topology resists local erosion. At compact dimensions, global features are less likely to be erased by weathering, plate tectonics, or the slow chemistry of decay. These are not promises of immortality, but hints of alternative durability. The hypothesis invites a new kind of archival imagination. Imagine that a process, natural or artificial, had arranged fields or curvature in such a way that its imprint sits principally in the geometry of internal dimensions. To a three-dimensional observer, the direct material artifacts might be gone, buildings dissolved, metals oxidized, organic traces vanished. Yet the signature might persist as a pattern in the distribution of local charges, subtle phase relationships encoded in crystal lattices, or even as minute departures from expected gravitational or electromagnetic behavior tied to the geometry of hidden dimensions. The detection would require a translation, turning differential measurements, anomalies, and statistically significant deviations into a readable narrative about past events. This hypothetical archive is maddeningly subtle, but not entirely fanciful. Physicists, working decades later, cast Kaluza, Klein ideas into more elaborate frameworks, higher dimensions in which forces unify, internal manifolds whose shapes determine particle properties, the compactified geometries of string theory, where the vibrational modes of tiny strings encode mass and charge. Each development amplified the original insight from the 1920s, that shape at tiny scales can govern the spectacle at large scales. The modern versions are mathematically richer and more abstract, but the emotional landscape remains similar. Reverence for the unity of description, anxiety about empirical inaccessibility, and a persistent hope that some small anomaly could be the whisper that corroborates a grand idea. The reaction of the scientific community to Kaluza Klein was itself instructive. The notion sat uneasily at the margins between disciplines, geometry and physics, continuous fields and quantum discreteness. In the immediate aftermath, attention gravitated toward pressing practical problems, formulating quantum mechanics, understanding spectral lines, and later building quantum field theory and particle experiments. Kaluza Klein lay like a map to a treasure chest whose lock no one could pick. Nevertheless, its influence seeped into the collective imagination. It offered a prototype, extra dimensions as a unifying principle, compactification as an invisibility cloak, and topology as a bearer of conserved quantities. There is a quiet melancholy to this history. The idea offered a new archive, a new way for continuity across geological time, but it also underscored human limitations. Instruments are finite, experiments are costly, mathematics can outstrip the reach of measurement by decades or centuries. The story of Kaluza and Klein is thus also the story of patience in science. Some hypotheses must wait while technology, technique, and the very questions a community is willing to ask evolve. In the meantime, the hypotheses serve as beacons. They shape the questions scientists think to ask of data. They suggest where anomalies might be meaningful rather than mere noise, and they push the interdisciplinary crossings, bringing mathematicians, particle physicists, cosmologists, and even geoscientists to converse in new ways. From the perspective of a speculative documentary about Earth and deep time, Kaluza Klein is a conceptual turning point. It is not a claim that the deep past is written into hidden dimensions. It is a proposal that such an archive is conceivable and, further, that the architecture of the universe might permit a kind of preservation beyond mere matter. It reframes the archaeological imagination. Not only must one look for sturdy artifacts, resistant isotopic signatures, or inexplicable geochemical anomalies, but one must also consider the possibility that the most enduring traces are geometric, imprints that require new modes of observation and interpretation. Moreover, the Kaluza Klein episode teaches a methodological lesson. It demonstrates how theoretical elegance can point to experimental targets, even if those targets lie far beyond present reach. The compactification idea predicts a tower of massive Kaluza Klein modes, a series of possible excitations corresponding to quantized motion around the small circle. In a modern accelerator, such excitations would appear as new particles with specific mass spacings. The absence of such detections constrains how large or small the extra dimension could be, but it does not disprove the core notion. In the geological context, similar logic applies. An absence of obvious Robust non-terrestrial signals does not rule out subtler geometric archives. It only narrows the parameter space of what such archives might look like. There is also a cultural resonance worth noting. The 1920s were a period when the limits of perception were becoming a public story. The idea of hidden structures accessible only to the mathematically trained or experimentally equipped fit into broader motifs of modernity. The confidence that human intellect could reveal nature's secret codes, and the complementary unease that much may remain unreadable. Kaluza Klein, in this sense, embodies both modernity's hubris and its humility. It is proof that with a changing conceptual posture adding a single dimension to the ledger, entire relationships can be reinterpreted. But it is also an admission knowledge is constrained by the senses and by the instruments organized by habit and funding. There are plausible structures in the mathematics that might only be confirmed by technologies not yet invented. To close this part of the narrative, one should not imagine a clean, triumphant arc. The Kaluza Klein idea did not settle the question of extra dimensions, it opened it. It shifted the conceptual ground, making it legitimate to think of forces as geometrical and of compact spaces as repositories. It prepared intellectual soil for later speculative architectures where the number and shape of hidden dimensions determine particle properties and perhaps, at an even more speculative remove, encode histories in their folds. The image that lingers is not that of an empire preserved intact, but of patterns pressed into a pliant medium. The medium is geometry, the patterns are symmetries and quantized momenta, the archive may be partial and the key elusive. But the simple audacity remains, to go beyond counting directions and to consider the possibility that the missing dimension is not an exotic extravagance, but a natural answer to a deep question of unity. This is the small, tremulous step that marked the emergence of the fifth dimension in modern thought, a step whose consequences would ripple through theoretical physics and, in the speculative imagination of deep-time archives, suggest new ways for the past to survive into the present. What follows in the story is the slow accretion of that idea into broader theoretical frameworks, its periodic revivals and adaptations, and the stubborn search for empirical signatures that might turn the metaphor into measurement. The Kaluza Klein moment is a hinge. It illustrates how a mathematical suggestion becomes a scientific program, and how the possibility of hidden geometry reshapes not only physics, but also the sense of what it means to remember. What if the most intimate architecture of matter, the pattern that decides what particles exist, how they interact, and how forces whisper across space-time was not written in atoms at all, but in the geometry of spaces too small to be seen? Picture the universe as an instrument, not a machine, strings stretched across an unseen frame, each vibration producing a tone that corresponds to a particle. Now imagine that the frame itself contains corridors and folds invisible to ordinary motion, corridors whose shapes dictate which notes are possible. This was the image that began to circulate quietly and then insistently through the halls of theoretical physics in the decades around the 1970s. It was an idea that both raised the stakes and deepened the mystery to make the music come out right. The instrument required more room than the familiar stage of three spatial dimensions. The origin of string theory was not born as a grand unifying philosophy, but as a pragmatic attempt to make sense of stubborn, experimental puzzles, patterns and hadronic scattering that resisted explanation by point-like particles. Mathematical structures that emerged in the late 1960s and early 1970s, amplitudes that behaved like resonances from oscillating entities, looked uncannily like the signature of one-dimensional objects. As the formalism matured, a startling realization took hold. When one quantized these extended objects consistently, the equations demanded an ambient space with more directions than those visible to the human eye. At first the count was extravagant, 26 dimensions for the simplest bosonic version. Later, when quantum consistency and the inclusion of fermions were required, the number reduced, yet still remained beyond ordinary intuition, 10 dimensions for superstring theories, and the suggestion of an 11-dimensional framework in the broader web that would later be called M-theory. There is a peculiar emotional texture to such a discovery. On the one hand, there is exhilaration, the almost narcotic pleasure of mathematical coherence. A piece of algebra that once scattered into unrelated terms reassembles into an elegant whole. Forces that once seemed unrelated begin to look like different, resonant modes of the same fundamental oscillators. On the other hand, there is a cold, professional worry. How does a theory that lives in 10 or 11 spatial dimensions make contact with a world that is palpably three-dimensional? How does one translate the poetry of higher dimensional geometry into the hard language of experiment? Technical answer was to propose that the extra dimensions are compactified, folded into shapes of such microscopic size that ordinary motion cannot probe them. The idea had precedence. Earlier, Kaluza-Klein schemes had suggested compact circles. String theory generalized this into an astonishing variety of internal manifolds. The vibrational spectrum of a string depends sensitively on the shape and topology of these compact spaces. A particular three-dimensional universe, with its specific particle masses and coupling constants, corresponds to a specific pattern of curvature and folding in the unseen dimensions. In this picture, geometry becomes not only the stage for dynamics, but the scriptwriter. Particle properties are the handwriting of shape. That handwriting can be extraordinarily intricate. The mathematical objects that first captured the community's imagination in the 1980s, Calabi-Yau manifolds, are complex, folded spaces with hidden holes and cycles that control how strings may wrap around them. Each cycle, each twist, fixes aspects of the low-energy physics perceived in three-dimensional life. It is a humbling, almost religious thought. The identity of electrons, quarks, and photons might be a consequence of which tiny loop threads through a minute fold. The analogy of an instrument becomes literal. Change the internal cavity, and the timbre changes. Change the manifold, and the spectrum of particles shifts. This dependence on geometry generated a heady sense of possibility and a parallel disquiet. If so much rests on unseen shape, then the landscape of possible universes becomes vast. The equations allow an enormous number of distinct compactifications, each producing different effective laws of physics in the large dimensions. This proliferation is seductive and disorienting at once. It suggests a plurality of potential histories, a multiverse of possible archives. But it also challenges one of science's most cherished aims, unique prediction. If the theory yields a profusion of consistent low-energy worlds, how does one extract the particular numerical fingerprint corresponding to the one human observers inhabit? The social and intellectual reaction was a blend of awe, impatience, and methodological reinvention. For many practitioners, string theory's promise was irresistible, a single unified framework that naturally included gravity and the quantum properties of matter seemed like an answer to a question physics had been nudging toward for a century. Yet the experimental silence pressed in. The characteristic length scales associated with string compactification, the so-called string scale or Planck scale, were tiny, many orders of magnitude smaller than anything accessible to accelerators. The excitement of a theoretical breakthrough coexisted with the frustrating prospect that direct tests might remain forever out of reach. The 1980s and 1990s saw the theory deepen in surprising ways. Object lessons accumulated. Strings were not the only possible excitations. Higher dimensional extended objects, brains, were recognized as crucial players. These brains could localize fields, sweeping the possibility space wider. Perhaps the visible universe itself is a three-dimensional brain embedded in a higher dimensional bulk. This reframing made some puzzles easier, about how matter might be confined while gravity spreads to extra dimensions, or how certain cosmological phenomena might leave imprints beyond standard expectations. The conceptual flexibility grew, and with it came new metaphors, universes nesting within universes, membranes carrying histories across scales, geometry bifurcating into layers of effective reality. The intellectual mood in these decades combined a rarefied thrill with a sober, sometimes melancholy recognition of limits. Mathematically, the structures were rich beyond expectation. Physicists found themselves squeezed into collaborations with mathematicians, anthropologists of formal thought, and cosmologists. Entire subfields, mirror symmetry, topological string theory, moduli stabilization emerged, each a small discipline of interpretation. Yet for every mathematical triumph there was a question about physical visibility. The community learned to live with a peculiar double life, a confident, sometimes aesthetic certainty about theoretical beauty, and a modest, patient deferral to the eventual arbiter observation. In the speculative frame of deep time and hidden archives, string theory introduces haunting possibilities. If fundamental properties are encoded in the topology of compact dimensions, then the preservation of information might not only depend on durable matter, but on the persistence of geometry. Geometry has habits. Global topological features are robust against many local erosions. A fold, a cycle, a hole, these are not easily smoothed out by surface weathering or chemical corrosion. In principle, then, a civilization or a natural process that used geometric manipulation as a means of inscription could create a record that resists the geological blender. Such an idea is not a claim about what actually occurred on Earth. It is a hypothesis about a class of mechanisms. That information could be stored in relational, geometric degrees of freedom rather than in fragile artifacts. The practical challenge is formidable. How does one detect a relic of a Calabi-Yau shape in a rock sample? What would a fossilized imprint of a compactified manifold look like in the geological record? The connection cannot be direct. It must be mediated through observable consequences, tiny departures from expected particle properties, minuscule anomalies in gravitational behavior, particular scales, rare patterns in isotopic ratios that refuse mundane explanation. Here, the narrative of string theory intersects with experimental ingenuity. Physicists propose signatures, Kaluza, Klein excitations that would appear as a tower of massive modes in high-energy experiments. Slight modifications of Newtonian gravity at sub-millimeter distances, exotic relics from the early universe such as cosmic strings or brain collisions that might leave gravitational wave signatures. Cosmology became a partner. The early universe is an amplifier, where processes at ultra-high energies could project their influence into the large. Even so, no single smoking gun detection has yet emerged. The absence is meaningful, not proof of absence, but a constraint that gradually carves away at the space of possible compactifications and mechanisms. There is an emotional undercurrent to this prolonged non-corroboration. For some, it is a chastening chastity, a reminder that mathematical elegance is not a substitute for empirical bite. For others, it is a call to expand the instruments of inquiry, to seek gravitational waves of ever subtler character, to push torsion balance experiments to smaller scales, to study the deep time record with new statistical eyes. The hope, quietly persistent, is that a sliver of anomaly, an inexplicable resonance in particle collisions, a pattern in ancient rock magnetization, an unexpected chirp in gravitational wave data might act as a key. That key would not prove string theory in a single stroke, but it could anchor a program of translation, taking mathematical structures and reading their shadows in the world. This brings the story to a philosophical hinge. If the properties of matter are functions of hidden geometry, then there is a sense in which the universe's history is encoded not only in the arrangement of objects, but in the shape that hosts them. That idea reshapes what counts as an archive. The geological record, stratigraphy, fossils, isotopes, remains indispensable. But it sits alongside a subtler geometric layer, a set of relational patterns that may survive in different ways. To pursue that layer requires new kinds of interdisciplinarity. Theoretical physicists must converse with geophysicists about possible macroscopic relics. Condensed matter physicists might develop analog experiments to realize effective compactifications of materials. Cosmologists must map early universe scenarios. That could imprint higher dimensional signatures in observable data. There is also an ethical dimension to this speculative archive. The more that human-made or natural processes can alter geometry at fundamental scales, the more responsibility attaches to such interventions. The act of encoding, if it ever becomes technologically plausible, raises questions about who controls the medium of memory, but such concerns are, for now, anticipatory. The immediate, practical imperative is methodological humility, to expand the set of what is considered a potentially meaningful anomaly, to refine measurements, and to resist the temptation to conflate mathematical beauty with empirical truth. String theory's tale, as it unfolded from the 1970s onward, is therefore not a tidy victory lap. It is a long, complex negotiation between the lure of unity and the demands of observation. It has enriched the conceptual vocabulary available for thinking about preservation across deep time, geometry as script, compact dimensions as vaults, vibrational modes as letters. It has taught the scientific community new forms of attention, to symmetries, to topology, to the possibility that the record of the past may be written in modalities that do not weather in the way that stone, bone, or metal do. The story ends, for now, with a patient imperative. If the past could be hidden in additional dimensions, then the modern task is one of translation and probing. Instruments must be sharpened, theories refined, and unexpected data treated as invitations rather than nuisances. Each null result narrows the map. Each small anomaly offers a possible doorway. Above all, the proposal reframes how humanity approaches the silence of deep time. The universe might be far stranger than a straightforward reading of fossils and sediments suggests. To listen for its subtler songs, to attend to the geometry under the visible, is to expand the very notion of what an archive can be. In that expansion lies both the thrill of discovery and the reminder of how small a single life is against the music of folded dimensions. What if the hidden dimensions of the universe were not featureless tunnels, but intricate cathedrals folded so tightly that a speck of dust could contain a cosmos? What if, in the quiet architecture of the infinitesimal, the recipe for particles and forces was written like an illuminated manuscript, text woven into the very folds of space? This image is the compass for the next inquiry, the Calabi-Yau manifold, a mathematical shape that became the prime candidate for the geometry of those rolled-up dimensions. It is where complexity and subtlety conspire, and where the possibility of a durable, non-material archive begins to feel like more than a thought experiment. To say Calabi-Yau aloud is to speak a name that carries both mathematical precision and poetic suggestion. These are not ordinary surfaces or volumes. They are complex manifold spaces that, on the smallest scales, look like copies of complex coordinate systems rather than the familiar real number grids of everyday geometry. That technical shift matters. Complex structures allow a kind of twist and interweaving that real geometries cannot easily emulate. Calabi-Yau spaces are also Kähler and Ricci flat, which, in physical terms, means they can support a balance in curvature that leaves the higher dimensional equations of gravity satisfied without, generating unacceptable forces in the dimensions humans inhabit. In short, they are mathematically hospitable places for strings to vibrate without tearing apart the fabric of the larger universe. The emotional effect of this fact is double-edged. On one hand, there is the sense of relief and wonder. Mathematics supplies a shape that is not only beautiful, but also compatible with the demands of quantum gravity and particle physics. On the other hand, there is a faint vertigo. These manifolds are extraordinarily variable. They come with holes and cycles, loops and voids that can be threaded by strings or membranes, and each topological feature influences the vibrational palette of the fundamental modes. In the sterile language of equations, changing a cycle changes a Yukawa coupling. In human language, changing a loop can change the mass of an electron. The idea that the identity of subatomic particles might be etched into corridors smaller than the wavelength of visible light is both humbling and disorienting. Calabi-Yau manifolds are described by discrete invariants, Hodge numbers, Euler characteristics that count independent cycles of different dimensionalities. These integers are like the integers stamped on an old ledger, simple, immutable, and telling. They constrain the ways strings can wrap and vibrate, but the manifolds also have continuous shape parameters, moduli, that tune sizes and angles of cycles, acting like the knobs of a cosmic instrument, adjust a modulus, and the low-energy physics felt in ordinary three-dimensional space shifts subtly. The twofold nature, discrete topological invariance plus continuous moduli, creates a landscape that is at once rigid and vast, hospitable to certain symmetries yet resistant to unique identification. The drama of Calabi-Yau geometry is not simply a mathematical curiosity. It is the bridge that translates minute shape into observable phenomena. The way a string winds around a particular cycle determines which vibration is allowed, and those vibrations manifest as particles with specific charges and masses. Fluxes, field lines threading cycles, can lock moduli into particular values, a process known as moduli stabilization. Brands, extended objects in which particles may be confined, can wrap cycles and alter the effective laws perceived at larger scales. The multiplicity of mechanisms means that a single Calabi-Yau shape can be dressed in countless physical costumes, depending on how fluxes and branes settle. The result is a deep interplay between topological permanence and dynamic decoration. The emotional tenor here is one of melancholy elegance. On the one hand, topology has the quality of durability. A hole is a hole. Cut a statue's surface away, and the presence or absence of that hole remains a global statement. Local erosion cannot change such a fundamental count. On the other hand, the continuous moduli are fragile. They can slide, wiggle, and respond to cosmological evolution. During the violent epochs of the early universe, moduli fields could roll, settle, or be frozen by thermal history. Thus, the potential for geometry to preserve a signature is nuanced. Some features are robust and could, in principle, survive grand upheavals. Others might be reset by the same processes that sculpt planets and crusts. This nuance is important for thinking about archives across deep time. If the identity of particles and forces is partly a function of topology, then topology is a kind of record less susceptible to ordinary chemical weathering than a bronze statue, but not immutable in every physical regime. The global features of a compact manifold, its Hodge numbers, the existence of certain homology cycles are candidates for durable information. They are the kinds of properties that survive local deformations. In speculative terms, if a process, natural or deliberate, left a non-trivial pattern in the topology of internal dimensions, that pattern might resist many modes of terrestrial erasure. It is not a promise of immortality, only the admission of a different modality of persistence. Mathematics supplied another surprise that deepened both awe and puzzlement: mirror symmetry. What began as a curious duality in string mathematics revealed that pairs of Calabi-Yau manifolds, wildly different in their detailed geometry, could produce identical low-energy physics. Mirror manifolds exchange counts of certain cycles and interchange complex with Kähler structures. The metaphors are of a landscape reflecting itself in a lake. The implication is profound. It undermines any naive expectation that a unique geometry corresponds to a unique world. The universe could be whispering the same physical tune while hiding the question of which exact manifold is the source. For the archival imagination, mirror symmetry introduces a disquieting possibility. Even if a relic imprint in hidden geometry were detected indirectly, reconstructing the original script might be ambiguous. The spectrum of Calabi-Yau possibilities swells still wider when topology change is allowed. Conifold transitions, surgical changes in the manifold where cycles pinch and re-emerge in different configurations, show that shapes can morph through singular phases. Physically, such transitions might be catalyzed by quantum effects or by energetic events in the early universe. In topological language, the space of all Calabi-Yau manifolds is connected by webs of such transitions, a vast, branching network often called the landscape. The existence of this network means that the geometry of hidden dimensions is not necessarily frozen forever. It can be rearranged by dynamical processes, and the history of such rearrangements might be written in other, subtler observables. This theoretical richness intersects with observable science in several ways. Some consequences of compactified Calabi-Yau geometries could, in principle, leave measurable traces. The presence of additional light scalar fields moduli could alter early cosmological expansion, leaving imprints in the cosmic microwave background or in the spectrum of primordial gravitational waves. Kaluza! Klein excitations, massive modes corresponding to motion around compact cycles, might, if their masses are low enough, appear in particle collisions as unexpected resonances. Topological defects or the dynamics of brains during cosmological epochs could produce relics such as cosmic strings, whose gravitational wave signatures could be sought by sensitive interferometers. Axion-like particles, often natural byproducts of compactification, could be components of dark matter and might be detectable in precision experiments and radio observations. Each of these possibilities offers a thread, fragile and narrow, by which hidden geometry could be probed indirectly. The difficulty and the human frustration that accompanies it stems from scales. The characteristic length scales of Calabi-Yau folds are typically thought to be near the Planck or string scales, orders of magnitude below anything that traditional geology or laboratory accelerators can resolve. The signatures that do trickle up into observable physics are indirect and often subtle. They demand extreme sensitivity, careful modeling, and an interdisciplinary patience that is not fashionable in a culture hungry for immediate results. The emotional climate this creates is a mixture of quiet hope and procedural steadiness. Hope that a tiny anomaly will act as a Rosetta Stone, steadiness to refine instruments, cross-check, and accumulate constraints. That is where the speculative archaeological imagination must be disciplined by method. To translate the possibility of a Calabi-Yau archive into an empirically actionable program requires concrete, testable hypotheses. One strategy is to ask what in terrestrial materials could reflect subtle changes in fundamental constants driven by moduli. Isotopic fractionations, ancient decay chains, and paleomagnetic records are all proxies that might show tiny, anomalous drifts in constants if those constants had been nudged by rolling fields in deep time. Another strategy is cosmological. The early universe, compressing and heating to extremes, is a natural laboratory where moduli fields and brain dynamics could have been excited. Remnants of those excitations, gravitational waves, non-Gaussianities and primordial fluctuations, or relic particle backgrounds offer the best chance of reading the record of hidden dimensions. A third strategy leans on particle physics. Precise measurements of rare decays, long baseline neutrino behavior, or high-energy scattering might reveal deviations traceable to Kaluza, Klein modes, or to extra light fields. Interpreting any such anomaly requires humility. A mismeasured isotope ratio can be dismissed as contamination. A noisy gravitational wave signal can mislead a missing resonance. In a collider search, tightens constraints but does not falsify the geometry. This is the scientific rhythm. Rule out ordinary causes, quantify uncertainties, build models that are falsifiable, and be willing to let the data slowly and sometimes grudgingly decide among competing explanations. It is also a communal task. The questions Calabi-Yau manifolds raise cut across disciplines. Pure mathematicians can enumerate topologies, string theorists can map their physical implications, cosmologists can compute relic signatures, geochemists and paleophysicists can seek small anomalies in deep samples. The work is an act of translation across languages, topology into particle phenomenology, mathematical invariance into geochemical fingerprints. There is a quieter ethical and philosophical afterword. To imagine that deep, folded geometry could act as a preserve of information, whether the record of a natural catastrophe or the trace of intentional inscription, raises questions about agency and stewardship at scales that dwarf human life. If geometry can host memory, should future civilizations shape it? If such shaping is possible, what responsibility does a species have to the preservation of potential archives? These questions are speculative now, but they serve a salutary function. They remind a science caught up in powerful instruments that the capacity to alter deep structure, should it ever arrive, would be an immense responsibility. In the end, the Calabi-Yau story returns to the human register that has been present from the first pages: smallness, temporariness, mystery. A tiny folded geometry, invisible to the senses and persistent in its topology, sits at the crossroads between mathematics and memory. Its holes and cycles, its mirrors and transitions, suggest that the universe can be both richer and more elusive than straightforward material narratives allow. The archipelago of possible shapes is a humbling counterpoint to human confidence. It asks for patience, for interdisciplinary curiosity, and for an aesthetic that can live with ambiguity. The final image is modest. Picture, briefly, a single cycle in a Calabi-Yau manifold, a loop, intangible and tiny. Picture that loop threaded by a field, steady through epochs when continents rifted and mountains wore away. No statue stands to record what passed there. No fossil bears the trace. Yet the loop persists as a topological fact. If the language of nature can be read at all, then such loops are punctuation marks in a sentence whose meaning slowly emerges when the right eyes and instruments, the right mathematics and patience, come together. To look for those marks is to accept a different kind of archaeology, one that listens for the whispers of folded dimensions and treats silence not as absence but as a map. What would it mean on the edge between metaphor and measurement? To admit that the universe's ledger did not stop at 3 directions of space and 1 river of time? What if between the folds of invisible geometry there were whole trajectories, worlds that might have been, histories that almost were, which sit not merely as abstract options, but as concrete spatial relations and dimensions the eye and the tape measure do not reach? That question opens the 6th chapter of this inquiry, a meditation on the metaphysical meanings of dimensions 5 through 10. It asks not only what physics might permit, but what it would mean for memory, identity, and the narrative of deep time if alternative scripts were folded into reality itself. Dimensions 5 and 6 occupy the first rung of this metaphysical ladder. In many technical proposals, some born of Kaluza-Klein intuition, others arising in brain world scenarios, extra compact directions can be imagined as small loops and handles attached to the familiar 3-dimensional scaffold. But metaphysically, they can also be pictured as parallel stages, spaces in which different choices, different initial conditions, or slightly altered physical parameters play out. These are not fairy tale parallel universes that hang free in a cosmic library. They are neighboring geometries whose boundaries, under the right conditions, can brush against the 3-dimensional world and leave traces. To hold this image is to feel a peculiar double emotion. First comes the quickening of wonder, the sense that history might not be a single line carved in stone, but a rich braid, many strands of which were never woven into the human story. Then follows a soft, communal melancholy, the knowledge that what might have been is often inaccessible, and that human time, the lifespan of civilizations, the memory of species, is minute next to the manifold of alternatives. Those emotions shape how the idea is both imagined and interrogated. It becomes less a metaphysical luxury and more a hypothesis with consequences. If 3rd and 4th spatial dimensions can hide entire structures, Why should fifth and sixth not encode parallel scenarios, Earths in which climates tip different ways, biospheres that assembled other ecologies, civilizations that took divergent paths in technology and culture? The metaphysical suggestion here is not merely narrative dressing. There are concrete ways in which such neighboring geometries could have observational consequences. Consider an extra-dimensional corridor folded in a microscopic loop. If a higher dimensional structure intersects three-dimensional space, the encounter could manifest as a localized perturbation, a brief, anomalous rearrangement of matter, an apparent violation of conservation laws at small scales, or a transient, gravitational irregularity recorded in the mineral fabric of rock. To a geologist, these perturbations might look like anomalous magnetizations, isotopic signatures that do not fit known processes, or abrupt discontinuities in stratigraphic layers that evade plausible terrestrial causes. To the philosophically inclined, they are the traces of unchosen possibilities. There is an ethical cadence to entertain as well. If alternate scenarios are spatially neighbors to our world, then the silence of those alternatives is not simply absence, but a kind of privacy. The metaphysical status of an unactualized history was it merely an unrealized potential or something with ontological weight? Shifts from abstract debate to a matter of stewardship. If mechanisms exist that could, in principle, let a motivated intelligence encode a story into extra-dimensional geometry, then the question of what is inscribed by whom and for whom becomes urgent. The deliberation is not hypothetical moralizing. It is an inquiry into the values that would guide any attempt to preserve knowledge beyond the ravenous appetite of geological time. A more subtle line runs between physical possibility and interpretive caution. The human impulse to detect a pattern can be voracious. Anomalies demand stories. Part of the metaphysical interrogation here is methodological humility. The idea that parallel scenarios could be folded into additional dimensions must be squarely set against the tendency to over-interpret anomalies. A strange isotopic spike is not automatically a message from a neighboring fold. More often, it is the geological record reminding observers of its complexity. Yet the possibility reframes the kinds of anomalies worth investigating. It broadens the list of suspects. Not only did volcanic outgassing or meteorite influx leave a mark, but perhaps a brief geometric intersection, a higher dimensional seam, altered local conservation relationships. The responsibility of science is to sort these hypotheses with care. Moving forward from dimensions 5 and 6, dimensions 7 and 8 invite a deeper metaphysical leap. They are the space where the plurality becomes not just a set of adjacent scenarios, but an entire family of histories, branching cosmologies, divergent physical laws, and distinct narratives of cosmic evolution. In certain theoretical frameworks, particularly those that arise in string and M theory, the extra dimensions do not merely provide room for additional forces. They determine the very constants and couplings that govern particle masses, interaction strengths, and symmetry breakings. Change the shape, change the physics. In that sense, dimensions 7 and 8 are not merely extra coordinates, they are the stagehands that tune the orchestra of the cosmos. The mental image is both beautiful and destabilizing. Imagine a catalogue of universes arranged by small topological variations. Move a knot here, open or close a handle there, and the low-energy physics that emerges, chemistry, stellar life cycles. The propensity for complex molecules to form shifts. The metaphysical implication is profound. What counts as laws begins to look like a contingent chorus shaped in part by hidden geometry. The plurality is not merely counterfactual, it is structurally embedded. Here, the emotional register tilts toward vertigo. The human mind is comfortable imagining a finite number of alternatives. It is harder to live with the sense that the landscape of possible worlds is vast, perhaps effectively endless, and that our own world is an island in a vast, topologically diverse archipelago. This notion has consequences for the meaning of deep time. The geological age of Earth, with its cycles of emergence and extinction, becomes an episode within a broader topological biography. Some histories in neighboring folds could feature Earth-like planets that never developed multicellular life. Others might host worlds where evolution ran faster or where planetary conditions favored different biochemistries. The metaphysical sting is twofold. For the first, it reconfigures human uniqueness, not by denying it, but by contextualizing it in a vast ensemble. For the second, it offers a refuge if the physical record in 3 dimensions is easily eroded. Perhaps the memory of other histories is preserved in part in the global features of higher dimensional topology. There is also a surprising intimacy in this multiplicity. If the extra dimensions set parameters, then changes in their configuration at cosmological epochs could leave coherent imprints. Across a range of observables, the early universe becomes a crucible where moduli fields, parameters that control the size and shape of compact dimensions, could have rolled, resonated, or been trapped, imprinting their dynamics in primordial gravitational waves or the statistics of density fluctuations. These imprints are physical documents, indirect, interpretable, and subtle. To the metaphysically curious, they are pages in a much larger book of histories. To the empiricist, they are testable possibilities, signatures to be sought with instruments sensitive enough to hear the faint reverberations from epochs when geometry was still being decided. One must not, however, confuse metaphysical possibility with metaphysical necessity. The space of mathematically permissible shapes is large, but physical realization depends on cosmological dynamics. Some regions of the landscape may be excluded due to instability, others accessible only through rare quantum transitions. The metaphysical lesson is therefore tempered. Plurality exists as possibility, but what was actualized in our causal past is constrained by physics, not whim. That reality is both sobering and freeing. It prevents cheap metaphysical expansion while leaving open the prospect that certain forms of information could be preserved in geometry rather than in fragile matter. The ethical texture of dimensions 7 and 8 thickens accordingly. If entire families of laws exist as alternative branches, then the act of discovering them raises questions about responsibility. The discovery of a method to manipulate hidden geometry, if it were ever to happen, would be tantamount to a form of creation. Choosing which effect of physics a region of space will exhibit. The moral stakes are enormous. Would a species ever be justified in altering deep structure, even with benevolent intent? The speculative philosopher sees an echo of older dilemmas about intervention in natural processes, but on an amplified stage. The possibility of inducing systematic differences, not just in ecology, but in the very rules that permit life. The narrative continues outward. Dimensions 9 and 10, in some theoretical accounts, host even more exotic possibilities. Not just alternative laws or parallel histories, but different modes of existence, degrees of freedom where relationships between causality, locality, and identity blur. Here, speculative metaphysics flirts with the edges of what language can hold. The suggestion is that in these higher folds, the categories that ground ordinary narrative cause leading to effect, objects maintaining persistent identity, may morph. For deep time thinking, that is both disorienting and clarifying. If higher dimensional regions can instantiate alternative ontologies, then the archive of existence is not only a tape of events, but a library of modes of being. That idea reframes how to interpret ancient silence. The fossil record records forms and transitions in a narrow ontology, organisms as bodies, time as sequence, mutations as discrete steps. But if other ontologies were available in adjacent folds, modes in which information persisted as relational patterns or as sustained topological invariants, then the absence of conventional artifacts is less damning. The metaphysical point is modest. Absence in one register is compatible with presence in another. This keeps the investigative spirit alive. It motivates a pluralist approach to evidence that seeks correlations across disciplines, high-energy physics data, gravitational wave surveys, detailed geochemical records, and comparative mythology. A final strand of reflection concerns the human affective economy. To live in a universe that plausibly contains neighboring scenarios and manifold histories is to live with a revised humility. There is the temptation to romanticize the plurality, imagining alternate eths as glorious cosmic backdrops. But the more useful emotional posture is restrained awe. Recognition of multiplicity does not trivialize human accomplishment. Instead, it deepens the sense of responsibility. If history might be preserved not only in monuments and layers of sediment, but in the shapes of hidden dimensions, then the methods of preservation, transmission, and interpretation must be broadened. The archaeological imagination must be taught new languages, topology, field dynamics, and the statistics of rare events. What follows, then, in practical terms, is an imperative for interdisciplinary translation. The metaphysical claims of dimensions 5 through 10 are not grounds for metaphysical indulgence, but for methodological expansion. Geologists, tasked with unpicking deep-time processes, might partner with theoretical physicists to identify which anomalies are meaningful in a higher dimensional framework. Cosmologists and gravitational wave physicists can scan early universe archives for the faint signatures of moduli dynamics or brain interactions. Philosophers must keep the conceptual questions sharp, clarifying what it means for history to be actual when multiplicity is baked into the geometry. And the public, who will eventually pay for and live with these explorations, must be prepared for the emotional mix of wonder and restraint that such inquiries require. In the end, the metaphysical meaning of dimensions 5 through 10 is not an easy moral or existential deliverance. It is a careful widening of perspective, a recognition that the archive of existence may be richer than the visible, that information can be encoded in folds and cycles as readily as in stone, and that the human task is partly translational, learning to read a language of geometry with the patience to sort signal from noise. The picture that emerges is neither consoling nor nihilistic. It is an invitation to attend to the possibility of parallel scenarios and manifold histories, is to accept that the silence of deep time is complex and that some of its quieter pages may be written in a script humanity is only beginning to learn. What if, somewhere beyond the calculus of probability and the tidy determinism of classical chains, there were not merely alternative explanations for one event, but entire, coexisting tapestries of history Earths that split like rivulets from a single stream of possibilities, each carrying its own set of outcomes, its own triumphs and erasures, the images at once intimate and enormous, a version of a life that took a different turn, a city that never crumbled, a climate that warmed or cooled by a few degrees, playing out beside the world that was. It is a hypothesis that nudges against the familiar edges of time and identity, an idea that certain frameworks in modern physics quietly permit, and that when extended into the scale of deep time asks unsettling questions about memory, contingency, and what it means for something to have happened at all. The many worlds reading of quantum mechanics offers the most disciplined, if audacious, way to take the notion seriously. In that interpretation, quantum events do not resolve into a single outcome by collapsing a wave function. Instead, the universal wave function continues to evolve deterministically, and what looks like a single outcome is simply one branch in an ever-forking tree. For every quantum decision, every spin measurement, every molecular collision that could have two outcomes, the universe's state becomes a superposition of distinct branches that decohere from one another. Each branch embodies a history with its own internal consistency. As decoherence sets in, those histories lose interference with one another and behave, from the inside, like separate classical worlds. There is an aesthetic elegance to this view. It converts quantum indeterminacy into abundance. Every possibility consistent with quantum amplitudes becomes, in some sense, real. The emotion it regularly provokes is a curious mixture, a peculiar uplift, like standing before an infinite shore and knowing that the tide has left footprints of every permutation, and a small, unnerving loneliness, since each observer, each culture, remains isolated within their branch. The many worlds perspective shifts the metaphysical weight of contingency. Rarity does not mean non-existence. It means inhabiting a less populous region of the branching forest. But the formal appeal must be translated into physical consequences if the idea is to matter for questions about deep time and hidden archives. For historians of the possible, there are two intertwined puzzles. First, what would it mean for parallel versions of a planet, variants of Earth, to exist as branches of a wave function? Second, could those branches ever leave detectable footprints in the branch that humans inhabit? The first question invites further specification. If branching is ubiquitous at the quantum level, then prima facie, there are unimaginably many near-identical worlds differing only by microscopic noise. More radically interesting are branches that diverge at macroscopic junctures, moments when a quantum fluctuation is amplified by chaotic classical dynamics into diverging histories. An asteroid striking a continent, a genetic mutation that cascades into a different developmental pathway, a climatic fluctuation that arrests or accelerates an ecological transition. Deep time is filled with such amplifications. Given sufficient opportunity, branches could describe entire alternative geological epochs. Yet bridging from metaphysical abundance to empirical evidence is fraught. Decoherence, the process that separates branches, works because environmental interactions quickly destroy coherent superpositions. For macroscopic systems, that very mechanism is why branches are effectively non-communicating. The human world appears classical because information about quantum phases disperses into reservoirs, air molecules, photons, thermal noise making distinct branches robust and autonomous. The practical upshot is disheartening for anyone hoping that a past civilization in a sibling branch might whisper across the divide. Branches, in ordinary conditions, do not exchange classical information once decohered. The branching is not a family of locked rooms connected by open windows. It is a house partitioned by walls that grew impossible. to climb as soon as the first gust of air swept through. Still, theoretical physics has not entirely closed the door on subtle interactions across what were assumed to be impermeable divides. There are speculative regimes, extremely contrived, technologically demanding, or cosmologically exotic, where communication or leakage might occur. Interference phenomena can be observed when branches remain coherent, but maintaining coherence at macroscopic scales requires isolating systems from their environment at levels vastly beyond. Contemporary capability, more intriguing from a cosmological standpoint, are mechanisms that involve the global structure of space-time. If the universe is not a simple, isolated Hilbert space but has topology or dynamics that permit non-trivial connections, wormholes, in the quantum gravitational sense, topological defects that couple branches, or interactions via fields that were never fully decohered, then traces might persist in measurable ways. Such speculations quickly intersect with the landscapes explored in earlier parts of this inquiry: extra dimensions, compactified manifolds, and the topology of hidden geometry. The metaphysical load carried by the many worlds idea can mingle with the topological richness of string landscapes. In some accounts, different low-energy laws correspond to different compactifications. In others, branches correspond to different quantum histories within a single compact geometry. The conceptual overlap is fertile. One can imagine that branching histories carve distinct macroscopic narratives while sharing a deeper geometrical stage. But the crucial point is that branches are distinguished by their decoherence histories. To decode a parallel pass from a branch would require a method that identifies signatures of improbable but uniquely geometrical or cosmological events, features that likely bear traces in universal observables rather than in local weathered artifacts. That reframes where to search. The geological record, for all its patience, is local and material. It remembers what made durable impressions and discards what did not. A collapsed civilization, however sophisticated, would be vulnerable to the same erasures as any other. Plate tectonics, chemical dissolution, biological recycling, branching world lines, by contrast, might imprint not on localized artifacts, but on statistical ensembles of cosmological relics. Primordial fluctuations in density, patterns of cosmic background and isotropy, the distribution of gravitational wave events, or isotopic ratios in deep reservoirs shaped by cosmological boundary conditions. All these are arenas where alternative histories could conceivably leave a mark that survives geological erosion. The search then becomes one of pattern recognition and universal data, not excavation of ruins. There is also a subtler epistemic route. Suppose a particular branch involved a macroscopic amplification of quantum randomness at a crucial moment in Earth's history, an event that would seed persistent anisotropy in the geological record, not explainable by known processes. That anisotropy might in principle be detectable as a pattern inconsistent with the expected statistics of natural processes, demanding cross-disciplinary scrutiny. But here the methodological burden is heavy. Earth's geological palimpsest is full of anomalies that eventually receive mundane explanations. The temptation to attribute every recalcitrant residual to a cosmic sibling is strong. Disciplined inquiry demands falsifiable models and conservative prize. The many worlds proposal thus functions more as a conceptual broadening of hypotheses to be considered than as a ready-made interpretive key. The metaphysical implications of accepting, even provisionally, the co-presence of near-identical or wildly divergent branches are profound. Identity, what it means to be a self, acquires a communal, almost democratic dimension. If countless near copies of events and persons exist, each inhabiting a distinct branch, does individuality shrink in moral or existential significance? The emotional response to this question is not uniform. For some, the idea induces an unsettling dilution of uniqueness, the sense that every choice is mirrored by versions that chose otherwise. For others, it is liberating, a cosmic empathy that connects lives across a forest of alternatives. From the documentary vantage, the more important enterprise is not settling how one should feel, but clarifying how such metaphysical possibilities shift responsibilities in scientific reasoning. If parallel histories are tolerated as admissible explanations, then evidence thresholds must be tightened and methodological pluralism embraced. Parallelism also invites new ethical reflections about legacy and stewardship. If, hypothetically, a mechanism were found to manipulate branching probabilities or to stabilize coherence across macroscopic histories, the capacity to preferentially actualize particular futures will be tantamount to deciding which histories get realized. the moral stakes would be enormous. Choosing among possible worlds would be a new form of intervention, one that touches on the deepest questions of agency and consent. These scenarios remain wildly speculative and ethically remote, but their conceptual gravity is instructive. They pressure contemporary discourse to consider the long-term implications of knowledge that appears, at first, as mere curiosity. The history of technology suggests that understanding often precedes wise use. Prefiguratory thought experiments help societies imagine governance before capacities exist. There is another angle where the notion of parallel worlds dovetails with cultural memory. Myths, recurrent archetypes, and the persistence of particular narrative motifs across isolated cultures have long been an object of study for historians and anthropologists. When treated cautiously, these cultural residues can serve as indicators of recurring observations. The idea that some motifs might encode, in symbolic form, impressions of anomalous environmental events is not novel. Extending that interpretive embrace to consider whether cultural imprints sometimes correspond to experiences of atypical physical phenomena that might themselves be artifacts of branching interactions is provocative but treacherous. It risks conflating metaphorical or social patterning with physical causation. The sensible middle path is one of disciplinary humility. Catalog myths and anomalies as potential guides, not proofs, and pair them with rigorous falsifiable physical models. Practical search strategies for traces of parallel or neighboring histories are consequently conservative and cumulative. The most promising arenas are those where cosmology and geophysics overlap, global observables that are both long-lived and wide-ranging. Primordial gravitational waves, for example, are relics of the universe's infancy that travel largely unscathed across epochs of chaos. If branching at cosmological scales accompanied grand reorganizations of geometry or the settling of moduli fields, then the stochastic gravitational wave background could encode signatures of those processes. Likewise, statistical anomalies in the cosmic microwave background, deviations from Gaussianity, hemispherical asymmetries, or localized cold spots, have been debated as windows into exotic early universe physics. None of these are smoking guns for sibling Earths, but they are the sorts of clues that could make the hypothesis empirically meaningful. At the scale of the planet, isotopic archives and paleomagnetic records are repositories of long-term processes. Slight, systematic departures from expected decay chains or secular variations in paleomagnetism that resist plausible geological explanations might, after exhaustive elimination of terrestrial causes, be considered as candidate evidence for extraordinary processes. The bar must remain high. Science's history is littered with anomalies that evaporated under scrutiny. But the existence of a non-trivial search program, one that brings physicists, geochemists, and statisticians into careful dialogue, would be a sign of methodological maturity. The quest would not be to prove the multiplicity of worlds in the metaphysical sense, but to map the constraints, to delineate what sorts of branching scenarios are compatible with observed data and which are not. Beyond empirical searches, the idea of parallel histories has an intellectual utility. It reshapes the questions scientists and historians ask of anomalies. It encourages the adoption of probabilistic thinking at planetary scales and invites the use of ensemble-based models rather than single counterfactual narratives. Deep time becomes less a single scroll to be read and more a distribution to be sampled. That shift is consonant with the broader modern posture described earlier. Geometry, fields, and topology are not mere background. They are active carriers of information. Parallel branching puts another layer over that realization. The archive of existence may be multi-stranded, and reconstructing its narrative requires tools capable of dealing with multiplicity. Perhaps the most human response to the prospect of parallel worlds is a renewed humility about the significance of silence. The absence of evidence for ancient, resilient civilizations on Earth does not settle larger questions about the presence of histories elsewhere in the multiverse of possibilities. Silence in the geological record is compatible with a richness of existence in other registers, geometrical, quantum, or cosmological. The right attitude for inquiry combines wonder and skepticism, speculative openness and methodological discipline. It is a posture that acknowledges human lives as brief flashes against a tapestry whose weave may be far more intricate than first appears. In the end, the hypothesis that parallel copies of worlds, and by extension of persons, exist beside the world that is, must be treated as an invitation rather than a proclamation. It widens the toolkit of explanation, nudges scholars toward interdisciplinary collaboration, and reframes silence not as pure absence, but as a complex signal demanding multiple modes of attention. Whether or not sibling histories ever reveal themselves as more than metaphysical possibility, the very exercise of imagining them sharpens the questions scientists ask of anomalies, encourages the search for subtle, universal relics, and deepens the ethical reflection about what it would mean to shape the future in a universe that might, at bottom, be a many-branched chorus of possibility. What if the cosmos is not a single vast ocean, but an ocean of many seas, each a separate place with its own weather, its own tides, its own slow geology, and the familiar universe that frames human life is only one swollen bubble drifting on that endless, dark surface? This image is simple and seductive, 1,000 billion spheres adrift in a cold, indifferent expanse. Yet beneath its simplicity hides a thicket of ideas that deepens the sense of smallness and mystery that has threaded the inquiry so far. The bubble multiverse is an idea at once grand and austere, an idea that rearranges the scale of contingency and the arena of possible archives. The bubble picture emerges from a solution to a concrete problem in modern cosmology. The early universe, in the inflationary account, underwent an epoch of runaway expansion driven by a high-energy field in a metastable state. In many inflationary models, that metastability is not uniform and eternal. Quantum fluctuations allow regions to decay into lower-energy vacua, nucleating bubbles of space that stop inflating while the surrounding background continues. Within each bubble, the rules, effective constants, particle spectra, symmetry breakings can differ. If the background inflates forever, this process produces an unending production of bubbles, a multiverse of causally disconnected regions, each internally coherent, each with its own macro history. Emotionally, the idea rearranges a familiar contour of human reflection. It amplifies the ancient humility about place into cosmic proportions. Not only is Earth a small stage on a single cosmic theater, but the theater itself is one theater among an uncountable menagerie. Yet, that amplification carries two competing sensations. On one level, there is the exquisite lift of possibility, the thought that many ways of being are instantiated somewhere, that the raw material of possibility is not just permitted by mathematics, but enacted in physical domains. On another level, there is a hardening of loneliness. The majority of those domains are forever inaccessible, sealed by causal horizons and the rapid divergence of histories. The bubble multiverse is thus a profound mixture of wonder and resignation. From a scientific vantage, the bubble picture is not mere metaphor. It supplies a mechanism by which different low-energy physics can arise naturally through the cosmological selection of vacua, and it produces a set of concrete, if elusive, signatures. Collisions between bubbles, for example, are inevitable in many realizations if inflating regions decay at a non-negligible rate. When two bubbles collide, the local geometry and field content can be violently rearranged. The immediate consequence in the collision zone is a disturbance in the curvature and the field values that could, in principle, propagate into the interior of the affected bubble as a permanent imprint. For observers living inside that bubble, if observers could survive, the imprint would be a misaligned patch in the cosmic story, a locale where the initial conditions differ subtly or dramatically from those elsewhere. Such collisions, if they occurred in our past light cone, might be visible as large-scale anomalies in cosmic observables. The cosmic microwave background, CMB, the fossil light emitted when the universe cooled enough for photons to escape a fog of plasma, acts like an ancient screen, a map of conditions when the universe was a mere 380,000 years old. Theoretically, a bubble collision could leave a circular or elliptical temperature modulation on that wallpaper, a localized departure from statistical isotropy. For a while, astrophysicists have scanned the CMB for such signatures, cold or hot spots, ring-like structures, or patterns inconsistent with standard inflationary fluctuations. The results to date are cautious. Many candidate features can be explained by mundane foreground contamination, instrumental quirks, or statistical flukes. Yet each search is a test, a promise that if a collision occurred early enough and with sufficient magnitude, the universe might still carry a readable scar. Another channel lies in gravity itself. Bubble collisions are violent rearrangements of stress and curvature. They can generate bursts of gravitational radiation. These will be primordial gravitational waves with characteristic spectrums set by the energy, scales, and dynamics of the collision. As gravitational wave detectors improve in sensitivity, scanning wide frequency ranges and building networks that triangulate directional information, the possibility opens that exotic, non-standard stochastic backgrounds might be detected spectral fingerprints inconsistent with known astrophysical sources, and suggestive of cosmological upheavals, for now the field is nascent. The detection of primordial gravitational waves would already be revolutionary, seeing structure within a stochastic background. That pointed uniquely to bubble-like collisions would be an order beyond that, a message encoded in the universe's deep time vibration. Yet there is an important sobriety to hold. The bubble multiverse idea is not a free-floating explanation for every anomaly. The same mechanisms that make a multiverse possible also impose constraints. Bubble walls sweep through space, rearranging fields. But the interior dynamics often smooth and thermalize collisions. The signal that survives to the CMB or to gravitational wave detectors depends sensitively on timing, on the contrast of vacua, and on the geometry of the collision. In many plausible scenarios, the signatures are tiny or washed away by later processes. In others, they could be dramatic but rare. The observational enterprise, therefore, must be patient, statistical, and conservative. Perhaps the most philosophically potent implication is a reframing of contingency. If every possible vacuum or near vacuum is produced somewhere, then the anthropic argument acquires a certain force. Observers will necessarily find themselves in bubbles compatible with complex structures. That is an unsettling closure for tidy explanatory ambitions. It shifts some questions. Why this particular value of a constant? Why this particular symmetry, from an expectation of a unique derivation to a probabilistic account of selection? The emotional effect is ambivalent. It is freeing in one sense, allowing explanation through selection and deflating in another, diminishing the aspiration to deduce particular values from first principles. This brings the inquiry back to deep time and the problem that has been recurring through this narrative: preservation. What, if anything, of other bubbles could intersect with the geological story preserved on Earth? The initial answer is simple and sobering. The vast majority of other bubbles are causally disconnected. Their interiors do not touch ours. But the boundary phenomena, bubble collisions, domain walls, phase transitions are mechanisms that operate at the interface between the cosmic many and the cosmic one, and they can leave relics that are not strictly confined to cosmological scales. In principle, a large enough collision could remold the field values in a substantial patch of space-time, altering constants or symmetry patterns locally. If such an event coincided with epochs relevant to planetary formation or biogenesis, the downstream consequences could be profound. Imagine, for a thought experiment, that a bubble collision modulated an effective coupling, constant in a region that later collapsed to form a star and planetary system. The altered chemistry might bias the synthesis of certain elements, change reaction rates, or nudge the distribution of isotopes. Over geologic time, those alterations would not necessarily look like messages. They would be anomalies, ratios, and patterns that stubbornly resist explanation by standard nucleosynthesis, volcanism, or meteoritic input. The geological record might then harbor hints, an isotopic spike, an unexpected abundance of a particular nuclide, a mineral phase that forms only under slightly different electronic structures. Interpreted conservatively, such anomalies have ordinary causes. Interpreted speculatively, they are possible scars of cosmological neighborliness. The sober requirement is methodological discipline. Extraordinary cosmological causes should be invoked only after exhaustive elimination of terrestrial processes. This is not just a philosophical demand, it is practical. The Earth is a noisy, messy archive. Plate tectonics shuffles layers, chemical processes fractionate isotopes, cosmic rays induce spallation, and life itself reworks chemistry at planetary scales. Only in instances where anomalies are globally coherent, cross-correlated across independent proxies, and statistically significant should cosmological scenarios be entertained. Even then, multiple lines of cosmological evidence, CMB marks, gravitational wave backgrounds, and particle physics anomalies would ideally converge to make a compelling case. There is another, more speculative mode of trace, the domain wall. In certain models, transitions between vacua are not clean bubble interiors but long-lived structures, walls across which the laws of physics change. If such a wall passed through a region of space, it will be catastrophic for pre-existing structures. But if it passed before planetary formation, it might set different parameters in adjacent domains. The wall could also trap relic particles, change the local dark matter content, or seed topological defects that later manifest as unusual magnetic textures in minerals. Here again, the logic is cross-disciplinary. To test such possibilities, cosmologists must model plausible wall dynamics and predict macroscopic signatures. Geologists must then scan for those. Predictions in deep time archives. A connected theme is the matter of information. Even if bubbles remain forever separate, The conditions that made our bubble hospitable were themselves selected by a larger cosmological process, the statistical distribution of vacua. The landscape contains information, albeit not information in the sense of a message inscribed by a prior intelligence, but information about what physical possibilities are realized. Detecting the statistical imprint of a specific class of vacua would amount to reading a page in a broader cosmological ledger. That ledger does not store human narratives, it stores possibilities and realized conditions. Yet this kind of reading is no less monumental. It would be a history written in the probabilities of physical law rather than in the shapes of stone. The bubble multiverse also reframes the ethical and existential questions touched earlier. If the cosmos contains innumerable balloons, each potentially harboring different permutations of complexity, then human meaning is neither magnified nor erased. It is contextualized. Some reactions to this reframing veer toward cosmic insignificance. Others see an expansion of belonging, a recognition that the universe is generative of variety on scales that surpass imagination, and that human inquiry is a fragile but sincere attempt at comprehension. The documentary tone here is to hold both reactions without collapsing them, to honor magnitude while insisting on the work of parsing evidence. Practical research agendas flow from that stance. Cosmologists will continue to mine the CMB for non-standard features, to refine statistical tools that separate fluke from signal, and to develop models mapping bubble dynamics to observable imprints. Gravitational wave observatories will push sensitivity curves and diversify frequency coverage, recognizing that primordial or exotic backgrounds are the next frontier beyond binary black hole mergers. Particle physicists will search for indirect consequences, unaccounted energy loss channels, anomalous relics, or patternings of fundamental constants that could point to phase transitions with cosmological provenance. Geoscientists, too, have a role to construct high-precision, globally correlated isotope records that could be cross-referenced with cosmological datasets. The search must be interdisciplinary, patient, and methodical. There is a final human image worth keeping. The bubble multiverse proposal is a kind of cosmological humility made explicit. It recognizes that laws in history that seem unique might be merely local expressions of a vaster generativity. Yet it also affirms the potency of narrowness. A single bubble, with its particular initial conditions, produces the complex tapestry of planetary geology, chemistry, and life. The silence in the geological record about ancient technological civilizations remains a blunt, important fact. The multiverse does not by itself solve that puzzle. What it does do is expand the catalog of what preservation could mean. Instead of only asking whether a stone or an isotope can survive 1,000,000 years, the question becomes whether a signature might be preserved in the curvature of space, in the statistics of primordial perturbations, or in the faint chorus of gravitational waves. The archive grows less parochial and more cosmological. When the documentary narrator steps back, the emotional chord is familiar, a mixture of smallness and resolve. The ocean of bubbles is both humbling and galvanizing. For those who listen, it calls for new tools, broader collaborations, and a patient curiosity that can keep company with both deep time and the vastness of possible worlds. The scientific work is technically exacting. The philosophical work asks for restraint and imagination in equal measure. The promise is modest but profound, even if the bubbles themselves remain largely beyond reach. The traces they may leave, if present at all, are the kind of deep-time relics that reward slow, interdisciplinary attention. To look for them is to practice a particular kind of humility, the humility of a species that admits its perceptual blind spots and decides, nonetheless, to keep scanning the horizon. What does it mean when a machine that was designed to listen to the sky reports a sound that seems to come from inside the planet? That single anomaly, a little blip of radio frequency arriving with an angle and a polarization that do not comfortably fit any known catalog, can open 1,000 doors in the imagination and 100 more in the inboxes of skeptical scientists. It was such a blip that set off a peculiar cascade of debate and experiment in the polar quiet. A report from Anita, a balloon-borne antenna array floating above Antarctica, saying it had seen energetic particle showers that appeared to emerge from the ice and move upward into the sky. The observation read, at first glance, like a paradox. To many it was a minor glitch. To others it was an invitation to rethink the map between theory and observation. ANITA, an acronym that sounds almost friendly in a way modern physics rarely feels, was built to do something straightforward and sublime. It listened from high above the frozen continent for the faint radio chirps produced when ultra-high energy particles slam into matter. The technique relies on a well-understood mechanism. When a high-energy particle interacts in dense media, it produces a cascade of charged particles that emits coherent radio emission. The instrument was tuned to catch downward, going cosmic ray air showers and the rarer radio pulses that portray neutrinos skimming the Earth's surface. Most of the openings in the data were exactly as expected, bursts consistent with cosmic rays arriving from above, reflections, and the statistical noise of a complex instrument. Then there were the upward-going events, pulses with arrival directions that implied an origin beneath the horizon, signals that, if interpreted naively, demanded a particle that had traversed thousands of kilometers of dense rock and ice and retained enough energy to produce an air shower as it emerged. That conclusion ran up against the wall of established physics. The Earth at those energies is mostly opaque to ordinary neutrinos. Even neutrinos interact weakly, but at the ultra-high energies Anita was sensitive to, the interaction cross-sections rise, and the probability of a neutrino passing through the whole planet without being absorbed becomes vanishingly small. The arrival angles and energy suggested an upward-moving tau lepton scenario. A tau neutrino enters the Earth, interacts near the surface, produces a tau lepton which escapes and decays in the atmosphere, creating a shower that Anita could see. On paper, this was a possible channel. In practice, the numbers did not add up easily. The effective flux of such tau neutrinos, as constrained by other detectors and theoretical models, should have been too low to produce the handful of upward events Anita had flagged. Out of that quantitative mismatch sprang a garden of hypotheses. Few papers argue for mundane instrument-based explanations: radio frequency interference, reflections off the payload, misreconstruction due to complex polarization effects. Others, more adventurous, suggested new physics, altered neutrino interaction cross-sections, a new particle that propagates differently through matter, or even exotic ideas that brushed against metaphysics, particles leaking into extra dimensions, or a fleeting connection to physics beyond the standard model. Among the more attention-grabbing proposals was the suggestion that an effective mirror or alternate vacuum might have altered particle propagation in ways that, if true, would force a rethink of deep assumptions about space-time. The response from the community was immediate and intense. The press, hungry for a headline that would drape science in mystery, seized on the more exotic interpretations. Opinion pieces proliferated, blog comment threads thickened, and for a moment the public imagination, enticed by the romance of another universe lurking beneath the ice, ran faster than the sober pace of replication. This is the anatomy of scandal-turned-discovery in the information age. A small signal amplified by human appetites for narrative, shaped by the media's taste for singularity. The scientific community reacted with something more measured, a rigorous skepticism that felt almost like a ritual, an established choreography designed to separate noise from signal. One voice in that choreography was Stephen, a name that, in the context of this episode, was less a single man and more an emblem of method. Stephen's posture was characteristic of a certain kind of scientific character, broadly curious, literate in both theory and instrument, and uncomfortably comfortable with doubt. He did not rush to the pulpit. Instead, he folded the anomaly into a longer conversation about how experiments, particularly those that push into regimes of low counts and high energies, should be interrogated. For Stephen, the Anita events were a textbook case of how the community should respond to an oddness that flirted with revolutionary implication. He began by insisting on the hierarchy of explanations. A signal born in a detector goes through layers of potential contamination, instrumental quirks, calibration errors, environmental interference, and then astrophysical processes. The prudent path, Stephen argued, was to weed these out carefully before elevating the result to the category of new physics. This was not merely pedantry. History provides a litany of near-revolutionary announcements that dissolved under closer scrutiny. Faster-than-light neutrino claims that evaporated when an improperly seated cable was replaced, signals in detectors later traced to mundane sources. The social memory of these false starts is not an embarrassment so much as a lesson. Extraordinary claims require extraordinary chains of evidence. That insistence on chains of evidence is where experiments became decisive. Anita's upward-going events were cross-checked against what other instruments could say. Ice Cube, the deep ice Cherenkov detector embedded in the Antarctic ice, has proven to be a formidable neutrino hunter. If Anita had seen a flux of ultra-high energy tau neutrinos that could traverse the Earth and emerge, then Ice Cube, or the Pierre Auger Observatory in Argentina with its enormous surface array, should have seen correlated signals or placed strong limits that made Anita's interpretation improbable. Those comparisons mattered because they transformed the problem from a single instrument anomaly into a test across a network. Statistical consistency across instruments is the language scientists use to translate eccentric data into reliable knowledge. Engineers and experimentalists went to work in parallel. Hardware teams re-examined Anita's signal chain, revisited calibrations, and subjected the entire detection pipeline to stress tests. Simulations of radio emission from upward-moving showers were refined. The way polarization rotates in the atmosphere, bounces off ice, or is distorted by the payload's own structure was modeled with greater fidelity. The air above Antarctica is not a passive medium. It is a layered mix of refractive properties, wind-swept surfaces that can act like radial mirrors, and, at times, human activity far more prosaic than the theories guessed. The instruments are sensitive, but sensitivity is both a gift and a temptation. The richer the data, the more ways for subtle systematics to masquerade as signal. At the same time, theorists engage the anomaly not as a provocation for fantasy, but as an invitation to define predictions. If some new particle or interaction were at play, what else would follow? Would it lead to deviations in high-energy, cross-sectional measurements elsewhere? Would there be a characteristic energy spectrum or angular distribution? Most importantly, could any of these follow-on predictions be tested with existing or soon-to-be-built instruments? Here, the dialectic of theory and experiment displayed its best self, speculation constrained by testability, wild ideas reshaped into concrete searches. Publicly, the debate was often raw. Social media distilled complex scientific disagreement into binary narratives. Some commentators portrayed the Anita team as discoverers of evidence for another universe. Others branded the whole episode as a cautionary tale about scientific overreach. The tension between public appetite for the sensational and science's slow hunger for replication created an uncomfortable pressure. Funders and institutions, watching attention metrics and fundraising opportunities, sometimes nudged toward more dramatic pronouncements. Stephen's temper of skepticism felt like a small, calming wind in that storm. The hope of the community that curiosity would not be traded for premature certainty. Over months and years, the Anita anomaly passed through many filters. Some instrumental explanations grew stronger. Investigations into payload reflections and peculiar radio frequency artifacts offered plausible pathways by which a downward-going cosmic ray reflection might be misreconstructed as upward-going. When a system sits on the fragile edge between direct arrival and reflection, small misestimates of geometry, of polarization, rotation, or of local index of refraction gradients can flip a conclusion. Independent tests, laboratory pulse injections, directed transmission experiments, and comparative runs under different environmental conditions moved the discussion from speculation to methodical closure. Yet the story resisted a tidy ending. For some anomaly hunters, the residual tension, the small fraction of events that remained difficult to reconcile fully with instrument effects, was a tantalizing thread. It kept alive the productive tension that drives science forward, the recognition that not all data fit the reigning paradigms and that sometimes those oddities point to genuinely new territory. This is the space in which careful, often unglamorous work thrives, building next-generation instruments, designing harsher falsification tests, and calibrating statistical methodologies to quantify how much of a departure from expectation is real and how much is a product of vagaries and human pattern-seeking. Anita's episode also clarified a cultural point. Scientific imagination cannot be shut off without suffocating discovery, yet it must be guided by method. The most creative ideas in physics are born at the scene where data refuses easy assimilation into theory. But the community learned to temper that creativity with procedural discipline. When unexpected signals arise, the right response is not a race to the most sensational conclusion, but a program of interrogation that insists on replicability, cross-instrument corroboration, and falsifiability. Stephen's stance captured that delicate balance, curiosity held in one hand, method in another. Beyond the immediate technical quarrels, the debate around Anita touched deeper themes that this inquiry has been circling for. Sometime, how humans interpret silence, and how a species with a narrow sensory palette extrapolates about the unseen. The ice of Antarctica is a good metaphor for the geological record writ large, mostly quiet, occasionally punctuated by anomalous features that demand story. In deep time, the planet's memory is partial and biased. Small artifacts are swallowed, isotopic anomalies are blurred. In that context, a fleeting radio event detected high above the surface may feel like a cosmic telegram, either a misreading that science will clean away, or the first faint tremor of a larger truth about the universe's hidden architecture. That ambiguity is not a failure, it is the engine of scientific inquiry. Anomalies compel the community to ask new questions, to refine instruments, and to think laterally about what counts as data. Even when an anomaly dissolves into instrument error, the work invested yields valuable byproducts, better calibration protocols, heightened sensitivity, and a sharpened skepticism that prevents future errors. The philosophical lesson Stephen and others emphasized was not despondent. The proper relationship to mystery and science is a blend of hunger and restraint. The hunger opens possibilities. The restraint asks whether those possibilities are real. The Anita Contretemps also underscored the social arrangements that make science resilient. Peer review, conference debate, preprint circulation, and replication attempts do not always operate at the speed of human curiosity. They operate at the speed at which communities can marshal resources, build instruments, and design robust tests. That slowness is not an inadequacy, but a safeguard. It is the apparatus that has saved modern science from the seductive appeal of premature myth-making time and again. In the end, what held most scholars' attention was less a verdict than a method. Whether the upward-going Anita events were signatures of instrument idiosyncrasy, a rare astrophysical process, or a whisper of physics beyond the standard model, the episode demonstrated how evidence matures. It begins as noise, passes into anomaly, confronts a battery of explanations, and either dissolves into understood background or persists as a stubborn signal that reshapes theory. Stephen's quiet insistence on patience was the narrative's moral. To pursue knowledge is to tolerate uncertainty, to design tests that can cut across competing hypotheses, and to let data, after careful interrogation, decide which doors to open. For those who watch the slow work of science with the impatience of a culture that prizes immediacy, that process can look disappointingly incremental. But its increments build the scaffolding of durable knowledge. Anita's blips became lessons about the fragility of instruments and the resilience of method, about how speculative headlines can outpace careful inquiry, and about the ways in which human curiosity, when married to disciplined skepticism, moves knowledge forward. The episode did not resolve the deepest questions about hidden dimensions or deep-time archives, but it refined the tools with which such questions must be approached. To listen closely to this story is to hear a particular kind of humility, a scientific humility that recognizes both the vastness of what is not yet seen and the power of method to illuminate it. Stephen's lesson, quiet and insistent, was this: the universe will always offer strange notes. The job of a civilization that wants to understand its place in deep time is not merely to dream of grand unifying metaphors, but to build listening devices, to cross-check their outputs, and to keep the lights on for the patient work of translation. In that patience rests the promise that if there is a hidden ledger folded into extra dimensions or written into rare cosmic events, human inquiry will one day, slowly and methodically, find a way to read it. What if the flicker of a gut feeling, an unaccountable certainty that something will happen, a dream that later aligns with waking events, was not merely an idiosyncratic quirk of a human mind, but the faint echo of deeper physics? What if intuition, that intimate, stubborn sense of foreknowledge, were not purely psychological lore, but a phenomenon that could be modeled, constrained, and perhaps even partially explained by the same equations that describe black holes and the birth of the cosmos? This is the knot that Hawking, both the historical figure and the symbolic presence in the modern scientific imagination, pulled at. In his late work and public reflections, he stood on the shoulders of many pioneers of quantum mechanics, relativists who had taught him to read geometry as physics, and the more recent architects of string theory and its 11-dimensional air M-theory. In the slow, patient way that theoretical physics advances, Hawking's enterprise was not a single dramatic proclamation, but a programmatic extension. Take the mathematical lessons of higher dimensional unification, fold them into cosmology's probabilistic landscapes, and ask what kinds of observable shadows such an architecture might cast, particularly on phenomena that have historically been consigned to the margins of scientific inquiry, like premonition. There is a peculiar melancholy to even imagining such a project. The cultural image of intuition is intimate and private. It lives in the boreal fog of memory and emotion. The attempt to put it on a ledger of equations risks desiccating a human experience into parameters and operators. Yet, Hawking's approach was not an act of reduction alone. It was a disciplined extension of the program that had carried physics beyond classical limits. Ask whether seemingly subjective phenomena admit formulation as statistical correlations, whether they obey conservation principles, and whether they leave traces that could be measured, even weakly, across the indifferent machinery of geology and cosmology. At the core of that move is a mathematical scaffolding borrowed from M-theory's conceptual repertoire. M-theory, as it was articulated in the late 20th century, is less a single equation than a web of dualities, a recognition that various string theories are different limits of a deeper 11-dimensional framework where membranes, higher dimensional branes, and geometric fluxes play central roles. In such a space, the identity of a low-energy particle and the character of a physical law depend on the topology and geometry of the hidden dimensions. Hawking's speculative step framed as a question that could be formalized was this: if physical information can be stored in geometric features beyond ordinary three-dimensional experience, could processes that connect branches of quantum history or momentarily couple distinct regions of a multidimensional manifold produce informational correlations that feel at the human scale like premonition? The mathematical mechanism he explored was not the stuff of cheap mysticism. It begins with the recognition that quantum mechanics is, at base, a theory of correlations. Entanglement ties degrees of freedom across distance. Decoherence explains why macroscopic branches appear classical. What if, in a universe with extra compact dimensions and a complex topology of vacua, there were rare, though well-defined, processes that transiently revived coherence across branches or permitted tiny, structured transfers of phase information? In M-theoretic language, the relevant actors would be moduli fields, brane intersections, and topological tunneling events, mathematical processes that, in the high-energy early universe regime, already have known physical consequences. The leap was to ask whether analogous, albeit immensely weaker, processes could occur at later cosmological times, and whether a sufficiently sensitive chain of measurement, crossing neuroscience, geophysics, and high-energy physics, could detect their residual fingerprints. Thinking this way produces a cascade of emotions in the narrator's voice: reverence for mathematical generality, the cool thrill of unification, and a grounded skepticism about scale. Hawking's models were elegant in the way good mathematics tends to be, the kind of elegance that invites metaphors about keys and locks, ciphers and translations, yet they also brought with them the stubborn arithmetic of attenuation. Even if a brain process could, in principle, imprint phase correlations across a local region of spacetime, the energetic and entropic costs of maintaining coherence in a warm, wet, noisy planetary environment are forbidding. The signal would be staggeringly small. The question then becomes not simply whether the effect is possible, but whether it could be amplified or channeled into the perceptual apparatus of a brain or into any durable geophysical archive. Hawking's tentative answers did not imagine brains as mystical antennas tuned to higher dimensional radio. Rather, the models proposed concrete, if narrow, channels through which higher dimensional physics might couple to macroscopic systems. One class of mechanisms involved rare instances of topological flux fluctuations, minute changes in the configuration of compact, cycles in internal geometry that alter effective couplings for ephemeral instants. Such events, occurring within a localized cosmological patch, could modify reaction rates or decay probabilities very slightly. The expectation would be not miraculous predictions, but statistical biases, a marginal increase in the likelihood of certain outcomes in narrowly defined circumstances. Another channel drew on entanglement and decoherence theory. In quantum mechanics, correlations can extend across systems without any transfer of energy in the classical sense. If degrees of freedom that influence neuronal microstates became entangled, however faintly, with a larger scale environmental field shaped by hidden geometry, then a brain's probabilistic state might, in principle, be correlated with remote events. The key word is correlated, not causally invoked. That distinction matters ethically and scientifically. Correlations are a legitimate part of physical theory. They do not imply backward causation or violation of locality in any naked sense. What they do allow is for a conditional predictive edge. Given certain boundary conditions and a known prior, an agent might update their credences in a way that produces statistically significant premonitions relative to blind chance. Hawking was particularly attentive to the statistical framing. He insisted that any serious hypothesis about premonition must specify the null model, the chance distribution against which observed predictive success is judged, and produce testable, falsifiable predictions about rate sizes, environmental dependencies, and energy scales. This is scientific rigor dressed in the clothes of empathy. To engage phenomena associated with subjective experience is to insist that the standards of testability are maintained, not relaxed. The search strategies that flow from this program are eclectic and necessarily interdisciplinary. If premonition-like correlations are mediated by subtle changes in coupling constants, then one practical approach is to examine long-lived geochemical records for small, coherent deviations in reaction products clustered around times when reported premonitory experiences spike in human communities. That sounds fanciful at first hearing, but it is a methodologically conservative statement. Look for cross-correlations between independent data streams, human reports, geological proxies, and independent cosmological observables. The requirement of independence is crucial. An anomaly that appears at once in isotopic ratios and in contemporary gravitational wave background measurements would be interesting. One that appears only in anecdotal testimony is not. Another line of inquiry lies within neuroscience and psychophysics. If certain neuromicrostates are more easily nudged by environmental quantum correlations, then well-designed, double-blind experiments could search for statistical predictability above chance in controlled settings. These experiments are notoriously difficult. Small effect sizes, the need for massive sample sizes, and the daunting task of eliminating experimenter bias. Hawking's insistence on mathematical modeling is helpful here because the models specify the expected scaling laws. If a hypothesized channel has an effect that falls off exponentially with ambient temperature or with the number of degrees of freedom entangled with the environment, this imposes strict boundaries on what an experiment can hope to detect. In short, the theory gives the experimenter a budget, what is feasible to detect and what is vanishingly improbable. High-energy physics and cosmology enter the program as well. Many of the processes that could generate the requisite topological or entanglement fluctuations are tied to events in the early universe or to the dynamics of fields that remain active cosmologically. Hawking's models thus point to signatures in primordial relics, tiny distortions in the spectrum of the cosmic microwave background, subtle non-Gaussianities in primordial density fluctuations, or a faint structured component in the stochastic gravitational wave background. Detecting such signals is already a primary goal of modern cosmology. The novelty is to interpret them with caution and humility, as constraints on mechanisms that could, in principle, mediate the kinds of correlations that register as intuition at human scales. This is where the tone of restrained wonder shifts toward ethical consideration. If some physical processes can, in principle, create correlations that humans might read as premonition, what responsibilities accrue to scientists and to publics who might exploit that knowledge? Hawking's voice in these meditations is not paternalistic, but practical. The revelation would not be an easy tool for prophecy. It would be a faint probability enhancer, a whisper of conditional information. The real ethical hazard is in overclaiming, constructing social systems that reward the illusion of predictive power and thereby erode trust in institutions built on testable evidence. The proper response is to urge transparency, rigorous statistical methods, and cautious public communication. There is also an aesthetic dimension to the inquiry. To think that human intuition might be tied, however weakly, to the geometry of hidden dimensions is to imagine memory reconceived. The geological record has always been a ledger of matter. This proposal expands the ledger to include, in principle, patterns of correlation embedded in fields and topology. That does not mean that premonition is a reliable archive. Far from it. The patterns are sparse, fragile, and subject to misinterpretation. But the idea reframes silence. A society that reads deep time only for bones and stones may miss a subtler class of signatures. The work Hawking advocated was precisely that, to widen the aperture of what counts as a plausible relic without surrendering empirical discipline. Opponents of the program raise powerful concerns. The dominant objection is one of parsimony. Extraordinary claims about new physics that supposedly account for premonition often introduce complex mechanisms when far simpler cognitive explanations suffice. The right response is to treat those cognitive models as the default hypothesis and to demand rigorous statistical elimination of mundane explanations before elevating exotic ones. Hawking's own methodological stance reinforced this conservative starting point. Theoretical creativity was permitted, but the evidentiary bar remained high. Another critique concerns the potential for vague theorizing to drift into unfalsifiable metaphysics. To prevent that slippage, Hawking's models were crafted to produce distinctive quantitative predictions, correlation magnitudes, energy scale dependencies, and cosmological signatures. If the models are not capable of specifying such markers, they remain metaphysical curiosities. If they do specify them, experiments can, in principle, rule them out. That is the virtue of a mathematically grounded program. It converts wonder into a sequence of constraints. The human dimension? The urge to find meaning in faint intimations of the future remains the thread that ties the story together. Hawking's work in this narrative is not a program to reduce poetry to calculus, but an insistence that poetry and calculus can coexist in productive tension. The possibility that premonition could be partially explained by physics does not denigrate the lived quality of intuition. Rather, it invites an attitude of humility and curiosity. Humility about the limits of present instruments and imagination, curiosity about the kinds of evidence that would move speculation toward knowledge. What would success look like? It would not be a single, splashy experiment. It would be a web of convergent constraints, a consistent statistical anomaly in tightly controlled psychophysical experiments, corroborating geophysical signatures that cannot be accounted for by known processes, and cosmological relics whose structure aligns with the predicted dynamics of moduli or brain processes. Only by such convergence could the community justify revising its priors about what the human mind can detect, and about the subtle ways the universe stores information. Until then, the tone remains patient. Hawking's program, mathematical, precise, and provocatively open-ended, served as an intellectual urging to expand the set of what is investigated without abandoning the hard discipline of falsification. It is an invitation to interdisciplinary humility, to let cosmologists and particle physicists, neuroscientists and geochemists, statisticians and philosophers speak to one another in careful, quantified ways. The possibility that intuition is not pure whim, but sometimes a reflection of deeper correlations, is a hypothesis that humbles as much as it excites. It reduces mystical allure and increases the demand for method. In the quiet, reflective cadence that this documentary voice favors, there is a concluding image that fits Hawking's blend of rigor and wonder. Picture a vast mathematical landscape, folding and unfolding in an 11-dimensional geometry. Within its folds are pockets, some of them active, some dormant, where fields and brains dance. Occasionally, in the rarest of moments, the dance touches a small island of matter, a nascent brain, a cooling crust, a rock forming a new layer. The contact is slight, an almost imperceptible modulation. To a species shaped by stories and pattern-seeking, that modulation might register as a premonitory glimmer. To a scientist, it is a measured correlation to be pursued with instruments, equations, and humility. To both, it is a reminder. The universe keeps more kinds of accounts than one ledger can hold, and the patient human enterprise of inquiry must learn, slowly and carefully, how to read them. What of the most unsettling possibility of all is not that the universe hides more space or stranger matter, but that it hides design of a very different kind, an architecture not of stone and field, but of instructions and subroutines. What if the laws of physics are more like code than creed, and the persistent enigma of deep time is not merely what has been lost to erosion, but what has been deliberately abstracted, compressed, or obfuscated by a computational substrate beyond direct reach? That question opens the 11th door of this inquiry. It is an idea that behaves like the others discussed so far. It is at once simple to state and fiendishly difficult to test. The simulation hypothesis, the notion that the cosmos might be an engineered computation, has become, in recent decades, a social and philosophical mirror for anxieties about technology, cognition, and the human appetite for explanation. In the register of a speculative documentary, it must be approached with both imagination and restraint. It invites the same pairing that animated the archive of geometry thought experiments, wonder at what could be, and humility before the limits of what can be known. The emotional texture of the simulation idea is recognizably complex. For some, it is a consoling possibility. If the universe is a computation, then history, however rarefied, might be recoverable through the right decoding tools, if only one can find the margins of the program that leak information. For others, it is an affront to meaning, a reduction of human narrative to a set of executed instructions, the unsettling sense that agency is a byproduct of code. Between those poles sits a third response, more characteristic of scientific habit, curiosity tempered by suspicion. How could one hope to distinguish a physically real cosmos from a very convincing emulation? What empirical signatures, if any, would mark a simulation? The first step in the documentary narrator's work is to translate the philosophical into the empirical. A simulation is, in effect, a system that computes outputs from a finite set of rules and data. Any computation must obey resource constraints, memory, time, precision. If the universe were a computation, then those constraints might manifest as anomalies and observables. That is the meat and potatoes strategy scientists use. Map metaphysical claim to measurable consequence, then search for the mismatch between expectation and measurement. There are several broad classes of possible signatures. The most commonly rehearsed is discreteness. Computation prefers finite representations. If space-time, energy, or information are discretized at a fundamental scale for the sake of simulation efficiency, then experimental probes should, in principle, find departures from continuum assumptions. This is not in itself a novel demand. Many physical theories already predict discrete structures at the Planck scale, but simulation framing shifts emphasis. It invites searches for systematic, algorithmic patterns in what would otherwise be considered noise, preferred frames and high-energy scattering, lattice-like anisotropies at the smallest scales, or unexpected regularities in cosmic ray spectra that defy natural stochastic models. Another class of signatures is compression artifacts. Much as a compressed image carries blockiness or statistical biases where the compressor chooses economy over fidelity, a simulated cosmos might exhibit telltale simplifications. Perhaps certain interactions carry higher informational cost and are therefore sampled less faithfully, perhaps safe. Approximations are used for long-run dynamics that have negligible short-term effect. In such a world, one might expect to find domains where laws of physics shift subtly with scale, regimes where approximations crack, and the simulator resorts to higher fidelity calculation. The methodological challenge is enormous. To discern whether an apparent scale-dependent breakdown is a genuine anomaly of simulation or simply the unmodeled complexity of a natural process. A related idea is that of debugging science. Real software sometimes leaves anomalies, logs, repeated error patterns, or artifacts of early developmental choices. Translated into cosmological terms, a simulator might inadvertently leave traces in the form of parameter coincidences, unexpected symmetries, or localized irregularities that look like the imprints of testing. A curious mind need only look at some of the cosmic oddities catalogued by scientists, the fine-tunings of certain constants, the near-flatness of space, the peculiar coincidences in cosmological parameters, and ask whether they are accidents of natural law, selection effects, or hints of a deeper, engineered economy. Yet all these possibilities collide with a vexing epistemic wall. A sufficiently sophisticated simulator could, by design, make the simulation indistinguishable from a non-simulated reality. The creators, if they wished, could encode laws whose emergent behavior would precisely mimic the continuum, hide compression behind noise, and remove debugging marks. Detection, therefore, requires assumptions about the motives, abilities, or limitations of the simulators. One must be explicit. Any empirical test of the simulation hypothesis hinges on prior hypotheses about what the simulator is likely or unlikely to do. That is an uncomfortable inversion of the usual scientific posture here. The testability of the claim depends on conjectures about hypothetical agents. This dependence does not make the enterprise worthless. Rather, it reframes it. In the same way that earlier parts of this inquiry paired speculative mathematical architectures with concrete empirical targets searching for Kaluza, Klein towers, Calabi-Yau imprints, or primordial gravitational wave relics, so too can the simulation idea be directed into specific disciplined programs. Scientists can ask, given a bounded set of plausible simulator strategies motivated by computational economics, what signatures are robust across many strategies? Which potential anomalies will be hard to eliminate even by a careful simulator? Those are the kinds of questions that turn philosophical curiosity into experimental challenge. Information theory supplies useful constraints. The universe's capacity to store and transfer information is limited by physical quantities, entropy bounds, the holographic principle, the energy available to perform computation. If the cosmos is simulated, then the cost of representing the entire state of the universe at arbitrarily fine granularity could be prohibitive. One implication is that the simulator might preferentially store and compute only what matters for conscious agents or for macroscopic outcomes. This selective fidelity would produce a testable asymmetry, high-precision correlations where consciousness and complexity exist, but coarser behavior in barren regions. The practical upshot for paleoscience and deep-time archaeology is striking. If a past civilization's details were not relevant to the simulator's ongoing aims, they might be offloaded, compressed, or removed. Conversely, if some species or event were deemed significant, the simulation might preserve their statistical fingerprints at the expense of other records. That is a chilling twist on earlier hypotheses about preservation in geometry. The archive might be selected because the substrate itself chooses what to keep. There are more concrete experiments that have been proposed in physics circles. Some researchers have suggested searching for lattice-like anisotropies in high-energy particle distributions, patterns that might signal a computational grid. Others look for violations of Lorentz invariance or energy-dependent speed-of-light effects as potential markers of discretized space-time. Yet another line probes for algorithmic complexity in cosmic microwave background fluctuations, the idea that a truly simulated sky might be algorithmically compressible in ways a naturally random cosmology would not be. These are, admittedly, delicate tests. The history of science warns that small anomalies often evaporate under better instrumentation, and that pattern seeking can mistake human aesthetics for physical law. But the virtue of these proposals is methodological. They translate a metaphysical question into statistical hypotheses that can be examined and falsified. If the universe were a simulation, then earlier lines of speculation, extra dimensions, geometric archives, brain dynamics take on new meanings. Hidden dimensions might themselves be efficient means of encoding information. A compactified manifold could be, in the simulational analogy, a data structure, compact, topologically protected, and resistant to local perturbations. The Calabi-Yau holes and cycles that interest string theorists would read, in computational language, as stable indices features that can carry information across processes without being easily altered by surface-level dynamics like weathering. The Kaluza-Klein modes, which appear as heavy states in particle spectra, would be interpreted as memory arenas or checkpointed states in the simulation's bookkeeping. In this light, the speculative archaeology of geometry and computation becomes unified. Whether the ledger is written in folded space or in bits of a substrate, the question is the same. What persists, how, and why? That unity raises ethical and philosophical perches. If a simulation can select what to preserve, then questions of agency and stewardship reappear under a new guise. Who decides what is relevant? If the simulator is itself an artifact of another civilization, then its choices reflect their values, not ours. The possibility is humbling. Human narratives of meaning risk being nested inside priorities shaped by unknown others. The documentary voice must hold this bleakness without indulging defeatism. Humility is not nihilism. It is an ethical call to craft our ways of knowing with care, to diversify the modalities of preservation, and to be wary of overconfident claims about cosmic meaning. There is also a practical counterbalance. Even if human existence were contained within a computational substrate, the human project of discovery does not become futile. The simulated world remains our world in every meaningful way. It supports life, produces suffering and joy, and yields empirical regularities we can manipulate. The simulation hypothesis modifies rather than nullifies the imperative of science. Indeed, it intensifies certain research programs. If compression and selective fidelity are plausible, then cross-disciplinary efforts become even more important. Geologists, statisticians, cosmologists, and information theorists must collaborate to identify signatures that are robust to reasonable simulator strategies. The work would be painstaking, probabilistic, and ultimately conservative, sifting extraordinary claims through layers of independent confirmation. There is a distinct political and social dimension, too. Once a community entertains the possibility that the cosmos is engineered, narratives about destiny, uniqueness, or teleology can bloom in unhelpful ways. The temptation to read cosmic significance into every anomaly or to interpret every coincidence as an intentional marker is strong. For a public discourse that cares about evidence and policy, the crucial task is to maintain scientific standards while allowing philosophical imagination to expand the range of hypotheses. That balance is not easy. It requires clear communication about conditional claims and the standing of evidence, and a public education that frames simulation as one of several scientifically addressable possibilities, not a metaphysical trump card. The emotional rhythm of this contemplation returns finally to the human scale. Encountering the simulation hypothesis elicits the same constellation of responses that has animated the entire journey through. Hidden dimensions and deep time archives wonder at the breadth of possibility, anxiety at the slenderness of human perspective, and an enduring optimism about collective inquiry. The proper stance, echoed in the methodological lessons from Anita's glitches to Hawking's speculative rigor, is not to chase sensationalism, but to widen the aperture of what counts as plausible evidence. Look for pattern where none has been sought before. Consider computational parsimony as a legitimate physical constraint and, above all, be willing to let no results sharpen the questions. There is a final, quieter image that suits the tone of this closing chapter. Picture a ledger that is both digital and geometric, folded and serialized. Some of its ink is written in the curvature of hidden dimensions, some in the statistical structure of primordial noise, and some in whatever protocols a simulator may use to manage fidelity. Human investigators, in their smallness, are like archivists with partial keys. They can read marginalia and reconstruct chapters from fragments, but the full codex may be unreachable. That is both a limit and an invitation. The limit tempers hubris. The invitation energizes patient curiosity. If the simulation hypothesis were true, it would not dissolve the ethical weight of human actions. If anything, knowing, or merely considering the possibility that the archive of existence is selective should press communities to be more intentional about what they build and preserve. Whether the medium of preservation is stone, isotope, folded geometry, or bits in a substrate, the human task remains to care for what endures, to refine the methods by which truth is distinguished from accident, and to cultivate a public culture that values both imaginative scope and methodological rigor. The mystery remains. The simulation hypothesis is not a closed book, but a question in the grand library this inquiry has been. Leafing through an added shelf that reframes older volumes rather than obliterating them, it is a reminder that the human project of understanding is as much about asking better questions as about finding definitive answers. The proper conclusion, for now, is modest. There is no final verdict. There are only graduated programs of search plans to press at the seams where computation could leave a trace, campaigns to cross-check anomalies across instruments and disciplines, and a communal ethic to avoid narrative excess. In the end, whether the cosmos is a computation, a manifold of folded dimensions, a multiverse of bubbles, or some combination thereof, the resonant truth remains the same as it has been throughout this series. Humanity's knowledge is partial but improvable. The archive of the past is scarred by forgetting yet laced with clues, and the act of inquiry is itself an honoring of what is fragile and precious. The speaker's final note is not a claim of triumph, but an invitation to keep listening, to keep measuring, and to keep imagining, carefully, critically, and compassionately, until the quiet ledger of reality yields more of its margins to the light. Could the idea of parallel universes in 11 spatial dimensions be a literal truth, or merely a shimmering scaffold for human imagination? The question does not demand an immediate verdict. It asks, more usefully, what it would mean to take the possibility seriously and what the consequences of that taking might be. In the arc of the story that has been told so far, through Kaluza's tidy trick, Klein's quantum twist, the Calabi-Yau cathedrals of hidden shape, the wild architecture of string and M theory, the branching ontologies of many worlds, and the bubble multiverse of inflationary cosmogony, one fact comes into sharp relief. The question is less a binary and more a set of thresholds. It is about how evidence accumulates, how disciplines translate one another's idioms, and how a species with limited senses organizes the work of suspicion, invention, and eventual confirmation. At the level of physics, the standards are familiar. A mathematical model that invites extra dimensions becomes compelling, not by rhetorical beauty alone, but by making contact with what can be observed. That contact is rarely blunt. It arrives as a pattern in a noisy background, a tiny deviation in gravitational attraction at sub-millimeter distances, an unexpected resonance in a particle collider, a faint component of primordial gravitational radiation, or a statistical oddity in cosmic microwave background anisotropies. Each of these will be a breadcrumb, not the whole loaf. The cumulative logic of science relies on the accretion of many breadcrumbs, independent, reproducible, mutually constraining. It helps, then, to be concrete about the kinds of traces one might expect if extra dimensions or parallel cosmologies were real. In more than metaphorical senses, the more straightforward predictions are the ones already being hunted. Kaluza, Klein towers in high-energy collisions, tiny departures from Newtonian gravity at micrometer ranges, axion-like particles whose existence is naturally explained by compactified topology, and gravitational waves with exotic spectra that betray violent early universe events like brain collisions or bubble impacts. Experiments have been designed to probe these areas. The Large Hadron Collider pushed the energy frontier, searching for signs of massive excitations, tabletop torsion, balance. Experiments have pushed limits on fifth forces and submillimeter deviations, radio and microwave surveys, together with next-generation gravitational observatories, are refining the map of the early universe's relics. But the problem and the philosophical pivot of this entire inquiry is scale. If the relevant length scales are at or near the Planck length, or if the dynamics responsible for the signatures were most active in an epoch long before planets and fossils existed, then direct detection is intrinsically difficult. That difficulty is forced in intellectual widening. The search is no longer only where are the extra dimensions, but also what kinds of signatures could a higher dimensional imprint leave in the coarse-grained world of rocks, isotopes, and cultural memories? This is where the conversation becomes genuinely interdisciplinary. Particle physicists exchange language with geochemists, topologists speak with paleomagnetists, cosmologists consult archaeologists and folklorists. The geological angle is subtle and stubborn. Earth's long memory is incomplete. Most things are lost to heat, pressure, and chemical reworking. Yet it is not entirely forgetful. Minerals such as zircons can preserve isotopic ratios for billions of years, remnant. Magnetization in igneous rocks records ancient field reversals. Certain isotopes are created only under narrowly defined nuclear conditions and therefore can serve as fingerprints. If a hidden dimensional event altered fundamental couplings, however fleetingly, it could in principle skew reaction rates, alter decay chains, or change the balance of isotopic production in ways that might survive in isolated reservoirs. The challenge is statistical and interpretive. Disentangle such a hypothesized exotic signal from the host of mundane processes that also change those signatures. Here, the narrative returns to patience. The scientific community's response to anomalies, Anita's puzzling upward-going events, odd blips in neutrino fluxes, discrepancies in particle cross-sections has been to build cross-checks. Instruments that see different aspects of the same physics must be brought to bear in combination. Deep ice, Cherenkov detectors like IceCube, surface observatories such as Auger, balloon experiments, and orbital platforms. Cosmological searches add another layer, satellite missions mapping the cosmic microwave background with exquisite precision. Pulsar timing arrays listening for low-frequency gravitational waves, ground-based interferometers extending sensitivity to frequency bands where primordial processes might be audible. The work is cumulative and often slow. A null result tightens constraints, guides theory, and sometimes forces a conceptual shift. A positive deviation must survive every conceivable route to mundane explanation before it can be elevated to evidence for the exotic. There is an emotional register to this hard work that is worth attending to because it shapes how science proceeds. There is the exhilaration of possibility, the quickening in the chest when a pattern refuses immediate dismissal and could, if it persists, reorient whole swaths of understanding. There is also a recurrent strain of disappointment when anomalies recede under the microscope, when more careful calibrations reveal instrument artifacts, when elegant notions of unification meet the stubborn arithmetic of measurement. Those twin currents, hope and humility, are not opposites, but collaborators. They preserve both openness to extraordinary outcomes and a discipline that prevents premature coronations. Parallel to the purely technical labors are the interpretive enterprises that use non-traditional archives as guides. Thoughtful readings of mythologies and recurrent cultural motifs do not provide evidence, but they can point attention to places where real-world anomalies might cluster. Oral traditions that speak repeatedly of abrupt celestial events, sudden ground upheavals, or a rain of stones could, with rigorous cross-disciplinary vetting, form a heuristic that directs geological surveys. Such guidance is only useful if coupled with falsifiable models. A story leads to a testable geological hypothesis about a layer, an isotope, or a magnetization anomaly. The risk of overinterpretation is real, but the potential payoff, finding a coherent pattern across cultural and material records, makes interdisciplinary humility a pragmatic posture rather than a mere nicety. Technology, too, has become part of the story. Advances in machine learning, in the careful application of Bayesian inference, and in high-throughput data pipelines allow modern science to ask questions of data that previous generations could not. Anomalies can be sought at scales and in combinations previously impractical, multivariate analyses across isotope datasets, pattern searches in cosmic microwave background maps, or anomaly detection in gravitational wave spectrums. The same algorithms that extract faint signals from noisy environments in other domains can be repurposed here, provided the teams applying them maintain statistical rigor and guard against the seductive overfitting of wishful hypotheses. There is a moral and political dimension that cannot be ignored. If, hypothetically, there were reliable ways to encode information in hidden geometry, if a civilization could hide records in the folds of extra dimensions, the ethical questions multiply. Who decides what to preserve? What safeguards exist against the erasure or misuse of information that might survive far beyond the life of any species? Even the thought experiment forces reflection on stewardship. What should humanity do with knowledge and tools that might reach across deep time? These are not idle philosophical indulgences. They matter because the technologies that allow deliberate manipulation of matter at fundamental scales are likely to arise within societies whose choices will be shaped by values, incentives, and power structures. The ethical discourse must begin early, not as a constraint on imagination, but as a companion to it. There is also a cultural dimension to the open question. The possibility that the universe contains more structure than senses reveal invites a broader public conversation about what counts as evidence, about the limits of perception, and about the virtues of patient, cross-disciplinary investigation. Science communicators have a responsibility here to resist the temptation to sensationalize speculative ideas while also nurturing public curiosity. The narrative that extra dimensions are mere fantasy, or that the simulation hypothesis is the only provocative endgame, collapses complex debates into caricature. The more productive posture is one that holds multiple possibilities and that demands a clear taxonomy of claims, distinguishing mathematical consistency from empirical demonstration, analogy from mechanism, and imaginative conjecture from testable prediction. So where does this leave the original question? Is the 11-dimensional universe, or a manifold of parallel realities, fact or fancy? The most honest answer is provisional. The present evidence is suggestive in places, but inconclusive. Mathematical physics has produced compelling frameworks that make the hypotheses coherent and sometimes predictive. Experimental physics has designed incisive tests. Many have constrained large classes of models. A few anomalies have provoked exciting work, but none has yet produced the convergent, cross-validated pattern one would require for a confident claim. Geological and cultural avenues remain promising, but methodologically demanding. The absence of proof is not evidence of absence. It is a measure of how deep the scales and how insidious the erasures. Yet the lack of a final answer is not a failure. It is part of the productive architecture of inquiry. The question has reshaped disciplines. It has pushed particle physicists to think about long-lived relics and tabletop gravity. Tests. It has pushed cosmologists to refine predictions of non-standard gravitational wave backgrounds. It has pushed geologists and paleoscientists to consider new proxies and to embrace statistical thinking, and it has pushed ethicists and philosophers to ask what it would mean to manipulate or preserve information beyond the lifespan of civilizations. The search has enlarged the catalogue of what counts as a meaningful anomaly and has created a culture of disciplined curiosity. There is, finally, a human consolation. The possibility of hidden rooms in reality dimensions folded tight enough that they evade ordinary sight, or sibling histories that go their separate ways at quantum forks, does not diminish the significance of the lives that are lived visibly. Small acts, fragile monuments, and the careful stewardship of knowledge remain morally and practically consequential, whether or not they are preserved in geometry or in computational substrate. The drive to leave a trace, to make memory outlast entropy, is part of a species-wide impulse to be known and to know. That drive has animated the work recounted here, and it will continue to animate the patient investigations ahead. The door remains ajar. It is ajar because mathematics suggests paths worth walking and because instruments keep improving. LIGO and Virgo and their successors will listen to ever more subtle strains of the cosmos. Pulsar, timing arrays, and next-generation cosmic microwave background missions will refine the map of primordial processes. High-energy experiments, tabletop gravity searches, and deep interdisciplinary surveys of the geological record will chip away at the space of possible explanations. Machine learning and careful statistics will help sift signal from noise. And across all of that will be a cultural shift, an increasing willingness for specialists to speak one another's languages and to let anomalies be addressed collectively rather than hoarded within narrow disciplinary silos. There is no guaranteed revelation ahead, no certainty that a headline will one day declare 11 dimensions proven. But there is a promise that the pursuit itself widens the human capacity to imagine, to ask better questions, and to build better instruments. In that sense, the unanswered question has been a productive gift. It has loosened the grip of complacent explanation, opened imaginative avenues, and furnished a framework in which the ordinary and the extraordinary can be measured against the same standards. If anything counts as an answer at this stage, it is procedural and ethical rather than metaphysical. The truth about dimensions and parallel universes will be discovered or else constrained by patient, cross-validated inquiry conducted with humility and with an eye to wider consequences. The search itself trains a species in a new kind of humility, one that recognizes the limits of perception while refusing to accept them as final. The journey to illuminate hidden rooms in reality has already widened human imagination. Whether or not the rooms are ever fully lit, the act of seeking them has opened a door in the mind as large as any conceptual universe might ever be. The invitation is simple and enduring. Keep listening, keep measuring, and keep imagining, carefully, critically, and with the quiet courage that long projects require.